All right, we're beginning our reading on time series analysis, and I've debated doing this reading a number of different ways, only because it can be kind of confusing. The reading, the learning objectives don't allow me to tell the story the way I want. So I'm going to change it up this time. On this reading, I'm going to go by section of the chapter as opposed to by learning objective. And then I'm going to bring in the problems at the end of the chapter in between what I'm doing and tie the learning objectives to those. And I think that's going to make a lot more sense, because here's the deal with time series analysis for our purposes. A lot of the keywords in the learning objectives are explain, describe, determine, that kind of thing. Only one calculate, only one calculate, but in describing and determining and explaining, we will do some calculating, but it's not required. So we don't really have to go into the depths of time series because it can get thick and it can get complicated. We're just going to describe the models and when the appropriate time to use them, and a framework for determining, well, where do we start and where do we end up? That's what we're going to do. To set the scene, and this is going to help you out a lot, considerably, is right now what I'm going to do is I'm just going to contrast the difference between a multiple regression with a separate, unique, independent variable and a dependent variable versus a time series. And when I show you the time series, I'm going to show you why it causes many more problems and why we have to have different models. So in a typical regression, where we have an independent variable identified as x and a dependent variable identified as y, we hypothesize some sort of causal relationship, or at least some sort of relationship where we can observe changes in x, and those changes help us explain changes in y. So we would look at a sample, and across that sample would have different observations of x, and those different observations of x would be associated with different observations with y. There'd be some distribution of x with y at each observation, and we might get something that looks like this, and we can draw a line of best fit through those data points. So the key point here is our dependent variable and independent variable are distinct. Serial correlation in something like this will not affect the consistency of the regression coefficients that we estimate. Serial correlation will tell us that we have a missing variable. It will affect the value of B0 and B1, but not the consistency of them. Consistency meaning that they tend to move in the right direction when they're supposed to move in a particular direction. That they don't give one value of B1 for high values of X. We would expect a lower value for lower values. That's consistency. They'll be consistent in that respect, but you may not be able to interpret them until you add the missing variable. For time series, on the other hand, notice that we have this dispersion here. Now watch what happens with time series. For time series, what we have is we have some dependent variable y, which we're observing, but we have no causal relationship. We're not hypothesizing that there is some variable that can help explain the variation in y. We're just observing it over time. That's all we're doing. So there is no relationship here. So we have an observation, let's say it's GDP. We observe it at some initial time, then 1 quarter later we take a measurement, the second quarter, the third quarter. So while every variable of x that we get to, we might have multiple realizations of the y variable. For every time period, there is only one. We may only have one observation. So while there may be a distribution, while each observation is a random variable, we don't actually get to see the randomness. We only get to see sort of one instantiation of it. And what we want to do when we have this is we're looking to find a trend. So we might say that it looks something like this. So I'm going to put the letter T down to say that that's the first thing we're going to talk about is a trend. The problem with time series data is while we can get this sort of variation in the observations, this sort of distribution on each x, here's what we tend to get when you're dealing with time series data, is you'll get some kind of cyclicality, because if this is GDP, there's a business cycle, and while GDP grows, it sometimes tapers off, it comes down a bit, then there's an expansion, there's a peak, there's a contraction, a recovery, an expansion. So it does this kind of activity. So we'll put a C down for cyclicality. Here's the problem. All the errors are above the line. Then they're all below the line. Slightly above here, they're all below the line. All above the line. So what you're going to get is you're going to get serially correlated error terms. Well, that's a huge problem in time series. It's a much bigger problem in time series than it is when we're looking at causal relationships between independent or distinct independent and dependent variables. So we have to deal with that issue. We've got to deal with that issue. The second thing is that GDP is seasonal. We expect higher GDP in the third and fourth quarters and typically lower GDP in the first and second quarters. So you tend to get kind of sawtooth patterns like this along with the cycle. So you have this kind of seasonality going on within it. So I'm going to put an S here for seasonality because we have to deal with that seasonality. And finally, with time series, as with any regression that we do, there's a random component. But sometimes with a time series, when we're just observing variables over time, the random component may be all there is. There may be no T, no C, and no S, and just R, just a big random component. So we have to determine, first of all, are we dealing with a time series of data here that is nothing more than just a random series of observations that may look like something? So we have to test to see if we have something called a random walk. So there's a lot that we have to deal with here. Now, the second problem, the first one is the serial correlation on the error terms. We can typically deal with that. Another problem that we have to deal with is when we look at a series like this over time, we have a non-constant mean and variance. So let's have a look over here, and we'll see what we mean. Over here we have a certain sample, and there'll be a certain range over which we've observed x, and that will be associated with a certain range of y. If we take another observation from the sample, we may get something in here, or something in here, or here, or here, or here, or here. But overall, we would expect that we can have a constant mean in x. It's not going to significantly change the mean. We would expect that as we get more observations, our estimate of the mean, our x bar, draws closer to the true population mean, mu. Not so with time series data, because when we add the next one, it gets added to the end. And the next one, well, I shouldn't put it there, that's the trend line, it gets added to the end, and then added here. And then maybe the next one's here, and here, and here. So what happens is we have a mean that is non-constant. And if we have a mean that is non-constant, remember how we calculate our variance, right? It's the x that we observe, whatever variable we observe, minus the mean over n minus 1. Well, if you have a changing mean, you have a changing variance. So we have a non-constant mean and a non-constant variance. So we're going to have to do something when we see a series that's upward sloping like this. We're going to have to do something to transform it so that we have a constant mean and variance. If we do not solve this problem of serial correlation and this problem of non-constant mean and variance, we cannot say anything. So that lays out our problem. So as we introduce each model, we start to see, okay, well, the models we're looking at first, we're going to look at two. A linear and a log linear is to try to isolate that trend, say something about the trend. Then we're going to test to see if those models are valid by testing for serial correlation. If it's not, we have to move on and deal with that cyclicality to get rid of that. Then we're going to eventually deal with seasonality and eventually deal with randomness. But for the most part, we're going to try to come up with a model and transform our time series in such a way that we no longer violate the assumptions of linear regression. Because the time series, I'm telling you right now, does. Period. The majority of economic data and the majority of financial data and accounting data, the majority of it violates the assumptions of regression analysis. If we're looking at time series, it will. So we got to deal with that. There's our task. So we'll move on to section 3, where we look at the 2 trend models that we'll use throughout the rest of this reading. But we'll use it in different forms. But we'll just look at the models here. Linear implies that the dependent variable changes at a constant rate with time, and it looks like this. And it's the same as everything we've seen so far in regression. Yt is our time series, is our observation on a particular time, equals b0 plus b1t. Now note here, time is the independent variable, and time goes from period 1, period 2, period 3, all the way to period t. So if we want to know what the model predicts the observed value of y should be at time period 10, we would just substitute 10 in here and multiply b1 by 10 and add it to b0 and get a predicted value. The coefficient, the slope coefficient here, is called a trend coefficient. Often inappropriate for economic data, trends typically have changing slopes and intercepts over time. So on the last screen I said that if we're going to model trends, it is going to violate the assumptions of linear regression, and this does. What we can do when we model this, if the linear model has serial correlation, we move on to a log linear. If it doesn't have serial correlation, we kind of got lucky there, but if it does, we move on to a log linear. And here the dependent variable changes at a constant growth rate. So while something like, let's say we're looking at the quarter-over-quarter percentage change in inflation, might tend to look like this over time. It may tend to look like that. Well, a linear model may be okay for that, simply because we have a constant mean and a constant variance on this. You can see that if we look at the range highs and lows, we seem to have a constant variance on this. But if we look at something like GDP over time, it will tend to do this. Which means if we draw a trend line through here, we will get serial correlation. So if we use a log linear model, we may get rid of that. And the log linear model looks like this, where yt is equal to e to the power of b0 plus b1t plus the error term. And if we take the natural log of both sides, we get the natural log of the observation, whatever variable our time series is made up of, equals b0 plus b1t plus e, the error term. Notice that this and this are now identical. The only thing that is different is the form of the data that we're observing. So if this were GDP, we would take the raw number of GDP, take the natural log of that, and that would become our time series, the natural log of yt. And then we can estimate this being linear in the parameters. And then again, we test to see whether we have serial correlation. If we don't have serial correlation, okay. If we do have serial correlation, we must move on to AR models, autoregressive models. So let's just have a look at how we would determine whether or not we have serial correlation. And you'll recall from the reading on multiple regression, we have a statistic for that, the DW statistic, Durbin-Watson. So we have to have our error terms uncorrelated across time periods. And we can use the Durbin-Watson test on residuals for that. Whenever we're using a linear or a log linear model where our b1t is expressed as such, where our independent variable is just the time period, you can use the Durbin-Watson statistic. If we're using an AR model, whether it be AR1, 2, 3, whatever the case is, you cannot use the Durbin-Watson statistic anymore. So this is just one case in which we can use it here. And you recall our hypotheses were stated as such. Our null hypothesis was that the Durbin-Watson statistic was equal to 2. We do not want to reject that. We want to fail to reject that. That is saying, if we fail to reject it, it is saying that we have no serial correlation. And of course, the alternative is that it is not equal to 2. So I'm going to show you how to look up the values in the table. But first we need to know a few things. When we go to the table, we need 2 values. We need a k value and degrees of freedom. K is the number of slope parameters we're estimating. And degrees of freedom is the number of observations. If we're looking for a B0 and B1, we have 2 regression coefficients, but only 1 slope parameter. And we're going to find a lower and an upper value for the Durbin-Watson statistic. And you'll recall that anything below, we would have to reject the null. We would have to reject the null, which means we have serial correlation. Anything in between, well, it's indeterminate. We can't really say much. And anything above, of course, we fail to reject, which means we do not have serial correlation. So let's just take an example. Let's say we have 77 observations testing at a 5% level, and we estimated a regression with B0 and B1. So here our K is 1 because we have 1 slope parameter and the other is just an intercept. 2 regression parameters, 1 slope parameter. When we go to the tables, and I'll show you in the next screen, when we go to the tables, we'll find a lower and an upper value for the Durbin-Watson statistic of 1.6 to 1.65. So anything below 1.6 on the output from whatever statistical package we're using for the DW statistic, we would have to discard the model that we're currently using because we have serial correlation, and would have to move on and try to re-specify the model. Trend models will typically have correlated errors. So if you did a linear model and you then went to a log linear model, you may be able to clear that up. But if it doesn't clear that up, that's as far as you can go. You must move into the autoregressive models. Typically, that's what you'll end up doing. So if we end with correlated errors after taking the natural log of whatever value we're looking at, we still have correlated errors. We got to move on to a better model. Let's have a look at how we get that, how we read the table for the DW statistic. All right, let's look at how we read the table for the Durbin-Watson statistic. And this will be Appendix E in your reading. There's only one table, alpha 0.05, and here's our K's across the top. This is the number of slope parameters we have. We only have 1 slope parameter, K equals 1. Notice that we have DL and DU. There'll be a lower and an upper value for the Durbin-Watson statistic. Here's our degrees of freedom. And remember, our degrees of freedom is our sample size. We scroll down to 75. These 2 rows are under K equals 1. Our lower limit is 1.6. Our upper limit is 1.65. So if our Durbin-Watson statistic comes in below 1.6, we would need to reject the model. We have serially correlated errors. So that's basically how you read this. And we have K 1, 2, 3 all the way over to 5. And again, notice you have upper and lower limits. And notice what happens to the values here as your n increases and as your slope parameters increase. They tend to, if you look at this value, 1.57 to 1.78. Anything for a large number of slope parameters for a large sample size, usually around 1.55 to 1.6. Anything below that would be questionable. So a lot of times you don't really have to come to the table too often. You'll notice that there are very rarely do we get really that low. It's just like if K equals 3, K equals 4 with a small sample size, you'll get a lot of leeway in this. But if your sample sizes are, let's say, 30 and up, have a look at 30 across here. You'll notice that the lowest it gets is like 1.21, 1.14, 1.07. So if you're getting a Durbin-Watson statistic, anything below 1 for any size of observations over 30, you don't even have to go to the tables. You can pretty much conclude that you have a serial correlation. And especially if you've only got 1 or 2 slope parameters, notice that for 1 or 2 slope parameters, once you get above 17 on your degrees of freedom, you don't drop below 1 on the lower limits at all. So sometimes just eyeballing the Durbin-Watson statistic, if you see it as 0.93, you've got serial correlation. No need to even test it at that point. Okay, I said that I would tie the learning objectives to specific problems, and that's what we're going to do now. We're ready to look at our first, we have the background to solve our, well, not solve, but sort of delve into our first learning objective, LOSA. So this will help us deal with LOSA here, and LOSA has keywords calculate and evaluate. Calculate and evaluate. And we have a couple of problems that relate to LOSA. So let me read the learning objective so that we got it. Calculate and evaluate the predicted trend value for a time series. Model as either a linear trend or a log linear trend given the estimated trend coefficient. So I think that's fairly straightforward. By the way, In this entire reading, that is your only calculate and evaluate. Everything else is just describe. Describe, explain. I'm looking down the keywords here. Describe, describe, explain, explain, determine. But there's no other calculate. This is it. So I think that's nice and light, right? Let's read what we have. The civilian unemployment rate is an important component of many economic models. Table 1 gives regression statistics from estimating a linear trend. So we're looking at a linear trend in this one, model of the unemployment rate, and here is the model derived statistics for. And what do we got here? Estimating a linear trend in the civilian unemployment rate, monthly observations, January 96 to December 2000. That is inclusive of the years. That is 5 years of monthly observations, 60 months. Great. Here's our regression, R squared. Really nice fit. The standard error. Observations. It looks like we were intended to solve the observations. Well, we know it's 60. Let's go ahead and put that in. Look at our Durbin-Watson, 0.9099. Now that we know the chart, we're familiar with the table and the Durbin-Watson critical values. This is well below 1.9. So we know we're going to reject the null hypotheses that there is no serial correlation. We're going to find serial correlation. I think it's pretty obvious. Our intercept and our trend, look at the t-statistics. They're both significant, but we know that this has got serial correlation. It tends to bias the standard errors downward, and when you bias them downward, you get significant coefficients, even though they may not be. But these are really, really significant. So we might say they're so significant, maybe we can let it ride, but we'll see. A, using the regression output in the table above, what is the model's prediction of the unemployment rate for July 96, midway through the first year of the sample period? Well, July 96 is within our sample, so we call that an in-sample. We're going to do an in-sample calculation here as opposed to out-of-sample. So the first thing for A is let's get our equation down. What do we have? We have the UER is equal to our intercept, 5.5098, plus, because this is the model up here, plus B1, but B1 is negative, so we'll just go ahead and just put negative 0.0294 T. And we're asked for July of 96. So we just have to count. January, February, March, April, May, June, July. 7 months in. So our T is equal to 7. Equals 5.5098 minus 0.0294. Put a 7 in there. And we will get 5.304. And that's percent. So we expect the unemployment rate, the civilian unemployment rate, to be 5.304 in July, and since this is in sample, we can check to see how far off we were. B, how should we interpret the Durbin-Watson statistic for this regression? What does the value of the DW statistic say about the validity of a t-test on the coefficient estimates? We've all pretty much already answered this, but let's do it formally. So for B, our null hypothesis is that the Durbin-Watson statistic equals 2. Our alternative hypothesis is that it does not equal 2. So we need some critical values because we have our test statistic. We just need some critical values to compare it against. So we will extract a DL, lower limit, and a DU. And I'm not going to show the table, but if you go to the table and look it up, you'll get 1.55 on a lower limit and 1.62 on an upper limit. We knew from eyeballing this we were going to reject it. So we have serial correlation. We can reject the null hypothesis. We accept the alternative. Well, what does this tell us about the validity of the t-test? It tells us when we have serial correlation, those standard errors are going to be underestimated. The standard errors are going to be underestimated. They'll be biased downwards. And the smaller the standard error, the more likely you are to have significant tests, right? And we do. So we have to look at these results and say, yeah, they're significant, but they're biased downward. Now, they're so large that we might look at them and say, but they're so large that even if you double these or even triple these standard errors, you'd still get a t-statistic that says these are significant. So we're kind of on the fence on that one. Anyways, there's a linear trend, and the only calculate and evaluate for this one we had to do was find a predicted value based on this linear model for period 7, and evaluate what we think about the validity of the t-tests. Done. Okay, we're still looking at LOSA here, but we're going to sort of look at this model we did in problem number 1. This is problem number 2. Let's see what we have. Figure 1 down here compares the predicted civilian unemployment rate with the actual civilian unemployment rate from January 96 to December 2000. That's the linear trend that we just did. Notice there's our intercept, 5.5098, and this is negative 0.0294. So that's dotted line is our trend. This is our observations. The predicted results come from estimating the linear trend model, which we've already done. Yeah, we've done that. What can we conclude about the appropriateness of this model? And remember, I said at the very beginning, we have a couple of issues to deal with. We have the trend. We've extracted a trend. But we have two other things that are going to mess us up: cyclicality and seasonality. Well, what have we got here? Look at our errors. They're above the line here, but they're below the line over here. They come a little bit above, somewhat below, and then back above. So we have a bit of a cycle over this period of time, which causes our errors to be all correlated together up here. Then they're all kind of correlated down here. And what this is saying is that if we have an error that is below the trend line, the next one tends to also be below the trend line. The next one tends to also be below the trend line. Then they're kind of above for a while, then they're below, then they're above. If this didn't have serial regression, we would expect this around the trend line, all the way down. We would expect that kind of random pattern all the way down, but we do not have that. We have the cycle. That is very, very common with time series data. Is you will get a cycle. You will have serial correlation. That is called persistence. So the errors are persistently positive, the errors are persistently negative, etc. So persistence, therefore positive serial correlation. The model, this linear model, is not appropriate for making forecasts. So the Durbin-Watson statistic tells us that we can't rely on the validity of the t-tests. And this persistence is telling us that, you know what, we have a cycle around the trend, which means you cannot rely on the actual regression coefficients that we have. The model is not, you simply cannot use it. It's invalid at this point. We must move on to a better model. All right, this next question, question number 3, takes us sort of straddling LOSA and LOSB. So we could probably attribute this somewhat to LOSA and to LOSB. Remember, LOSA was to calculate and evaluate. LOSB is just describe. And what are we doing in LOSB? We're going to describe factors that determine whether a linear or a log linear trend should be used with a particular time series and evaluate limitations of trend models. And I think I've done a pretty good job at the opening on the opening screen of explaining the difference in the type of data. Would we expect to see data grow at a constant amount each period or at a constant rate? So inflation could be modeled as the inflation rate or as the price level. Well, the price level we would expect to see grow over time, whereas the inflation rate we would expect to be stable. Stability, we can use linear. Growth would use log linear. So let's see what we have for question 3. You have been assigned to analyze automobile manufacturers, and as a first step in your analysis, you decide to model monthly sales of lightweight vehicles to determine sales growth in that part of the industry. Figure 2 gives lightweight vehicle monthly sales annualized from January 92 to December 2000. So here we go. Well, you can see first of all the fluctuations in here, and it's quarter to quarter. This sawtooth pattern, that's seasonality. Here, if you look at this, you have kind of this going on, and if you want to draw a trend, you kind of have a trend that looks like that. So you have persistence here, persistence here. So what we're seeing here is there is an underlying trend. There is cyclicality to that trend, which will lead to serial correlation, and the sawtooth pattern is seasonality in the trend. So we got a lot of unpacking to do in this one. So we have an idea of what the data is. We're talking about sales growth. So our trend, do you think it's most likely to be a linear trend that we're going to deal with, or are we going to deal with a log linear trend? I think the data, sales, would tend to, we'd expect sales to increase or to grow at a certain rate over time. I'd be thinking log linear here, right? Monthly sales in the lightweight vehicle sector, sales T, have been increasing over time, but you suspect that the growth rate of monthly sales is constant. So we're being told the growth rate is constant, not the increase is constant. The growth rate is constant. It's screaming log linear, right? Write the simplest time series model for sales T that is consistent with your perception. Well, the simplest model I know is going to be the natural log of sales T is equal to B naught plus B1 T. There's the simplest model. Stated without the natural log, by the way, it looks like this. Sales T equals E to the B naught plus B1 T. And of course, if you want to be very formal, you'd put in the error term. We can also put in the error term here if we want to be very formal. That is the simplest model, consistent with what we believe. So, you can do an observation of the data and you could say, well, I do see a trend, but I do see cyclicality and I see seasonality in here as well. You'll see all these things. They should jump out at you. We're being told that we're looking at a growth rate, sales growth, and we're being told that we don't think that growth is a constant dollar amount per year, but a constant rate per year. It screams log linear. There's number 3. All right, let's move on to section 4, autoregressive time series models, and let's just think about how we got here. We looked at 2 trend models, the linear and the log linear trend model, and I said that you're probably going to find serial correlation at both levels, so that you're going to have to move on to an autoregressive model, most likely. And here we have to worry about something called covariance stationary series. So we'll get to that in a second. Let's introduce what an autoregressive model is, and then let's just jump right into that assumption because we got to deal with it right away. An AR model is a time series regressed on its own past values. That's why it's called autoregressive, because it's regressed on its own past values, a lagged variable of the dependent variable. So xt equals b naught plus b1 xt minus 1. So GDP in this quarter is some function of GDP last quarter. Well, I shouldn't say some function, but we're modeling it as that the value last quarter has something to say about the value this quarter. That is an AR1 model, a first order model. The 1 in here signifies how many lagged variables we have. Here we have 1. If we had another term in here, B2 plus B2 xt minus 2 plus the error term, this would be an AR2 model, 2 lagged variables. So you can generalize that up to P lagged variables. That's a Pth order AR model. Let's deal with this idea of covariance stationary. Let me show you a non-covariance stationary model. And when I do, you'll say, but most models will be non-covariance stationary, I believe. Yeah, they are. So let's look at GDP over time. That is non-covariance stationary. To be stationary, it must satisfy three properties. Number 1, the mean must be constant and finite in all periods. So we need something that tends along a line like that. So this is just not going to do because the mean is not going to be constant and finite in all periods. B, we need a variance that is constant and finite in all periods. And C, we need a covariance that is constant and finite in all periods. And the covariance is the time series is the covariance of the time series with itself for some fixed number of periods in the past or future, and it must be constant and finite in all periods. This clearly violates the first one. You don't even have to worry about B and C. Clearly, we don't have a constant mean. This would give us a constant mean. Now, we can have something like this. There you go. There's your constant mean. You have constant variance, and just looking at the frequency of the amplitudes, it appears that you have constant covariance over time. So how do we know whether we have a stationary series? Well, we would plot it and have a look. We're looking for some kind of constant mean we want to avoid things like this. Even though this has a constant mean, we can see that it does not have constant variance. Also, we'd like to avoid something like this, because that looks like we have two separate series in there. And where else am I? Where else? Let me just erase this, and I'll draw another one where it would not be a very good series. Let's say we're looking at something like this, and then it does that, and then it does this for a while, and then it does that. That would not be covariance stationary. So we want to make sure that our data kind of looks like this over here. Our time series looks like this, and you're thinking, well, if it looks like this, how do we get it to look like that? And I'll show you shortly how we get it to look like that. But there's the issue. We need covariance stationary. If we don't have that, if not, results will be invalid. The estimates of B1 will be biased. It can't be used. Nothing can be said about it. You simply have to move on. You have to fix that problem first. Okay, so we'll deal with that. We'll look at some ways to make a time series covariance stationary. The second thing that we still have to deal with, we got here because of serial correlation in the error terms. We can't get out of here until we solve that problem too. We still have to solve the problem of serial correlation. However, this time, we cannot test whether we have serial correlation by using the Durbin-Watson. Now, you can draw a circle around that and a line like that saying no Durbin-Watson here. Cannot do it. So you cannot use the Durbin-Watson statistic. But what you can do is you can test the correlation of the error terms. So what you would do is you would take the error term at time t, and you would do a autocorrelation with it against the error term at t minus 1 for all observations in your time period. Then you'd take the observation at time t and do a correlation with the error term at time t minus 2. And then you do it again for time t with the error term at t minus 3. And then again for t minus 4. And our statistical package will, whatever software we're using, we can ask it to give us those autocorrelations. So we're really looking for the autocorrelation with the error term at a particular point in time with the error term at some previous point in time, and we're hoping it's 0. So if we go back one period of time, 2 periods, 3 periods, 4 periods, and they're all coming up 0, then we don't have any serial correlation. So let's have a look a little bit in more detail about this little term. We're not going to actually calculate it. You just should be aware of how we're arriving at it, so that when we look at the output from the regression output, we know exactly what it means when we look at it. Okay, so just so that we understand exactly what it is that we're testing when we look at the output from any statistical package, you'll recall that a correlation between two distinct variables, A and B, is the covariance between those two variables divided by the standard deviation of A times the standard deviation of B, and that'll give us a correlation. Well, for what we're doing here, we're looking at autocorrelation, so there aren't two distinct variables. It's the correlation with the error term with itself at some previous period. This is the autocorrelation of the error term. Again, autocorrelation means correlation with itself. So it is the covariance of the error term at a particular time with the error term at another particular point in time period t minus k, whatever k happens to be, a lag of 1, 2, 3, 4, etc., divided by the standard deviation of the error term at time t times the standard deviation of the error term at time t minus k. Typically, this is the same thing. It's just the standard deviation of the error term, so our denominator just becomes the variance of the error term. And our numerator, of course, is still the covariance between the two. It's an it's a correlation, a covariance of the error term at one period of time versus another period of time. So what we're testing is that the expected value of the autocorrelation is 0, that we have no correlation with the error term with itself at any point in time. So we'll go back a lag. K will be a lag of 1, a lag of 2, 3, 4, etc. And our test statistic is we take whatever value of the autocorrelation that we arrived at, and we divide it by standard error is 1 over root n. 1 over root n being the number of observations in our time series. So the output we're going to get from a regression run will give us the autocorrelation, it will give us the standard error, and it'll give us the t-test, the t-statistic for this, and we just have to compare it against some critical value. So here's the steps that we basically go through. We got to this point because the linear and the log linear model using time as the independent variable still had serial correlation, so we moved on to an AR model. Step number 1, estimate an AR model. Typically, AR1 is where we'll start. Compute the autocorrelations with the different lags, an autocorrelation with the error term with itself 1 period back, then 2, then 3, then 4. And then we're going to test whether or not it equals 0. And if we reject H0, if we reject the null hypotheses, it implies that we have serial correlation and a misspecified model. Now you remember, if we have serial correlation, when we're talking about distinct variables, it tends to tell us that we have a missing variable. Well, it's the same thing here. You can think of it as saying, hey, you got a missing variable. So what would be the next step? It would be to go back up here and then compute an AR2 model and go through the steps again until we get rid of the serial correlation. So let's look at the example from the reading, example 4, and we'll do a walkthrough on that one. So I think a nice way to proceed from where we are is to look at it in an example. Example 4 in your reading is a really great example. So let's just go through it, and it has everything that we need in here. This is predicting gross margins for Intel Corporation. Analyst Melissa Jones decides to use a time series model to predict Intel Corporation's gross margins. So sales minus cost of goods sold over sales, that's gross margin, using quarterly data from the second quarter of 99 through the fourth quarter of 2013. She does not know the best model for gross margin, but believes that the current period value will be related to the previous period value. Once we cover the topic of mean reversion, you'll see that if we're modeling something like a ratio, like gross margin, or a current ratio, or something along those lines, you'll find that the autoregressive model is the appropriate model to use because of something called mean reversion. But I don't want to get into it now. Anyways, let's see. She does not know the best model for gross margins, but believes that the current period value will be related to the previous period value. She decides to start out with a first-order autoregressive model. Gross margin in time period t is equal to b0 plus b1 gross margin in time period t minus 1. So there's the first lagged variable plus the error term. So that is an AR1 model. Her observations on the dependent variable are from second quarter 99 through the fourth quarter 2013. Table 4 shows the results. Let's just get right to it. R squared 54.29, standard error. Observations 59, the Durbin-Watson. Do we pay attention to this now? Once we get to AR models, you ignore the Durbin-Watson. SPSS or Stata will still spit it out for you, but just ignore it. It's meaningless, so that we'll just ignore. Here's our coefficient and our slope coefficient, our B0 and our B1, standard errors, and here's our t-statistics. We can tell, based on those t-statistics, that we're going to have significance, so we can reject the null hypotheses that these are equal to 0. They are different from 0. And I want you to pay attention to this coefficient here, 0.7449. Notice that it is not equal to 1 and that it is less than 1. That's going to become important later on. Let's just pay attention to that. And for the intercept, notice that it is statistically significant. It is different from 0. That's going to become important later on as well. Look down here. Here's the autocorrelations of the residual. This is something you can ask your software to do. Once you're modeling an AR1 model, you're going to want this output. Because what we want to do is we want to check for significance down here. If we have no significance, we fail to reject the null. The null hypothesis is that the autocorrelation of the first lag is 0, the second lag, the third lag, the fourth lag is all 0. These t-statistics are fairly low, so we can be pretty sure that these are not significant, which means we do not have serial correlation. It appears we have a well-specified model. We have an AR1 model that we can say at this point, you know what, we're good. We're good. Let's just see what the narration here is. At the bottom of table 4, the first 4 autocorrelations of the residual are displayed along with the standard error and the t-statistic for each of those autocorrelations. The sample has 59 observations, so the standard error for each of the autocorrelations is 1 over root 59. You'll recall that was our denominator. It was 1 over root 59. So the standard error 1.1302. So we take the autocorrelation 0.1450 divided by 0.1302, and that gives us the 1.13. That gives us the t-statistic. Table 4 shows that none of the first 4 autocorrelations has a t-statistic larger than 1.11 in absolute value. Therefore, Jones can conclude that none of these autocorrelations differ significantly from 0. Consequently, she can assume that the residuals are not serially correlated and that the model is correctly specified, and she can validly use OLS to estimate the parameters and the parameter standard errors in the autoregressive model, which we have. The last paragraph gets into a little bit of what we're going to look at shortly, which is mean reversion. When I say shortly, we'll do a few problems and we'll come back to mean reversion. So you can read this part if you want, and it kind of leads in to what mean reversion is, and it's one of the nice features of an autoregressive model is that if your B1, this term right here, is not equal to 1 but is less than 1, you will have a mean reverting model. All right, this is problem number 4. It's going to look at covariant stationary series in a little bit more detail. And to do this, we're also going to take just a little jump ahead and look at the idea of first differencing. I know we haven't gotten to it, but I'll describe it in this context here. So we're on LOSC with this particular problem, and LOSC is explain the requirement for a time series to be covariant stationary and describe the significance of a series that is not stationary. So remember, for covariant stationary, we need 3 conditions. The first condition is that the mean, the second condition is the variance. Both of these must be constant and finite, along with the third condition, which is the covariance must be constant and finite. So if we look across here, do we have a constant mean? Well, it appears that that we do. Across here. Where we wouldn't have a constant mean is if it looked like this. That is not a constant mean. Whereas anything that looks like this offers us a constant mean, so we can say yes. Do we have constant variance? Well, it seems that if we draw 2 lines like this, it seems to fluctuate in between these 2 lines. What wouldn't be constant variance is if we saw something like this over time. We'd have 2 different types of series in there. So it looks like condition number 2 is satisfied. And for covariance, we can see that it seems to be fairly regular in its variation. Again, where it wouldn't be covariance constant and finite is if you had something that looked like this, where it looks like you have constant mean and constant variance, but if you look at the fluctuations, they start to increase dramatically, then they spread out, then they increase dramatically, then they spread out. This doesn't look like it has that. So just a visual inspection of this, we would say it appears to be covariant stationary at this point. So what this is, if we read this here, figure 3 shows a plot of the first differences in the civilian unemployment rate between January 96 and December 2000. And first differences is you're simply just taking a change in the unemployment rate, looking at the value this period minus the value last period. You're just looking at the incremental difference period over period, as opposed to looking at the entire total period over period. You're looking at the incremental difference. So let's say that we were looking at a series of sales, let's say, and let's say that we had 8 million, we had 8.2 million, 8.35 million, and 8.4 million. If we were looking at first differences, what we would have here is 0.05, this would be 0.15, this would be 0.2, and this is what we're modeling here. So we're saying that the first differences, if we have a linear or a log linear model that is not covariant stationary, we could take first differences. the first difference, and plot that and determine whether that appears to be covariance stationary. So A says, has differencing the data made the new series covariance stationary? Explain your answer. And I think we have explained our answer in reference to all three conditions. Remember, you need a constant mean, you need a constant variance, and you need a constant covariance. And of course, you can see the fluctuations in these are neither packed too tightly or spread apart too wide at certain parts. Maybe in here you might say, well, that gets a little wide, here it gets a little tight, there's a little wide, but overall it looks fairly constant. B, given the graph of the change in the unemployment rate shown in the figure, describe the steps we should take to determine the appropriate autoregressive time series model specification for this series. So, whenever we have our data, the first thing we want to do is we want to look at a graph of it and ask ourselves, what do we see? Which of these kind of variations do we see? And we want to see something that looks like this. If we have something that looks like this over here, we might take first differences and see if we can transform it into something that looks like this. Once we have that, what are the steps to determine what the appropriate model is? Well, we would start with an AR1 model, an autoregressive 1 model, an AR1 model. We would test the residuals for serial correlation, which we saw in the example 4 in the book. If we do not have any significant autocorrelations, then we have a correctly specified model. But if any of those autocorrelations are significant, then we move on to an AR2 model. And we model an AR2 model and move on from there. Now, why are we thinking that moving from an AR1 to an AR2 model will get rid of serial correlation? Well, think about it in terms of a regular regression where we have an X variable and we have a Y. Here's the X that we can observe, here's the Y that we can observe, and we're going to regress them. If the error terms here are correlated, it is telling us that we have a missing variable. We have a missing variable. Well, think about the autocorrelation of the error terms the same way in this particular respect. If the error terms are correlated, it tells us that we have a missing variable. But what are our two variables in this case? Our observed variable is xt. Our independent variable is xt minus 1. We would simply just add xt minus 2. And say, okay, well, maybe that gets rid of the correlation. And when we add that, what's going to happen to the coefficient beta 1 here? Well, over here, if without this in the regression, xt minus 1 is doing some of the work of xt minus 2. So when we add xt minus 2, the coefficient on here will tend to drop because xt minus 2 will give some explanatory power. So we'll get a better model, and hopefully we'll get rid of that autocorrelation in the error terms. All right, this is question 5. Table 2 gives the regression output of an AR1 model on the first differences in the unemployment rate. Describe how to interpret the DW statistic for this regression. And there's our Durbin-Watson statistic. So how would you go about interpreting that statistic? We look at our intercept and the change, the first difference in the unemployment rate for T minus 1. They look to both be significant in this respect, and the 2.18 is close enough to 2 for us to say there's no serial correlation. Be careful now, this is an AR model, an autoregressive model. What did we say about AR regressive models? You cannot use the Durbin-Watson statistic. DW cannot be used. So how do we interpret this? We simply don't. We don't interpret it, we ignore it. A little bit of a trick there. All right, let's talk about mean reversion. And before we get into it, let's go right down to the middle of the screen here. And you'll see that I've written in one line here, all covariance stationary time series have a finite mean reverting level. If they do not have a finite mean reverting level, they are not covariance stationary, and we're going to see something called a random walk shortly where this is not the case. And this is how we can tell whether or not we're modeling a time series that has something going on or whether it's just purely random. It will have a mean reverting level. All covariance stationary time series. Let's just get that out of the way. All right, let's see what this mean reverting level is all about. Mean reverting means that the value of the time series tends to fall when the series is above its mean, and it tends to rise when its series is below its mean. And again, remember, it's got to be covariant stationary, right? At a mean reverting level. If we're at a mean reverting level, what we're saying is that the value that we observe today in the time series will be the value we observe one period from now. So xt plus 1 we know is equal to b naught plus b1 xt. That's the lagged variable of t plus 1 is t. So we could just get rid of the xt and just solve for xt equals b naught plus b1 xt to find the mean reverting level, which is what we do. So if you just use algebra and you isolate xt to one side, you will get b naught divided by 1 minus b1. So for any time series that is covariance stationary, we can find the mean reverting level by simply taking the intercept and dividing it by 1 minus the slope coefficient. If the value of the time series is below the mean reverting level, our forecast of the next period value should increase towards that level. And if it's above that level, then our forecast for xt plus 1 using that value of xt should decrease towards the mean reverting level. So we're going to look at an example of that shortly in one of the problems. While we're here, let's look at the chain rule of forecasting. I think that this is so obvious and simple that it doesn't need to be said, that you could have figured it out yourself if there wasn't a name for it. So it basically looks like this. If we're looking for a 1 period ahead forecast, that means it's an out of sample forecast, so it is t plus 1. So in other words, we're looking to forecast t plus 1. And of course, if we're using a lagged variable, the estimate we arrive at for xt plus 1, now it's x hat, because remember now, we're not there yet. We're forecasting, right? So the forecasted value of xt plus 1 is b naught plus b1 xt. Here we can observe xt, and that'll give us some estimate of what we'll have 1 period out. A 2 period ahead forecast, again, we're estimating t plus 2. We have to use a lagged variable of xt plus 1, but we can't observe it yet. We can't observe xt plus 1 because we're only at period xt. So what we have to do is we have to take the forecast of xt plus 1 and substitute it in for the actual observed value instead. So the forecast for xt plus 2 is b naught plus b1 xt plus 1. But notice this is not an observed value now. It is just a forecasted value from the model that we had. So we can see that the further out we forecast, since we're not using actual values, we're using forecasts each time, and forecasts have error, these errors will begin to add up and compound. So that over time, the further out we try to forecast, the less accurate and the less confident we can feel that our forecasts are accurate. Well, I don't think that took a statistician to say. I think you could have said that. I think anybody could have said that, hey, listen, if I try to forecast what's going to happen in the next 20 minutes, I might be pretty close. But if I try to forecast what's going to happen 3 weeks from now, I'm going to be way off. Look at any 10-day weather report and ask me, or ask yourself, is the next day fairly accurate? And is the 10th day fairly accurate? Well, the next day weather forecast tends to be pretty close. But 10 days from now, it always changes. Well, so that's the same thing here. But the point I think that they're getting across this chain rule of forecasting is that if you're going to forecast out 2 periods, you must forecast first 1 period, substitute that in to forecast 2 periods. Then if you're going further, you'd use that, you'd substitute that to forecast the 3rd, you'd use the output from that as the input to forecast the 4th, you'd use the output of that as the input to forecast the 5th, and so on. All right, this is question 6. And where are we now? LOSF. This ties well to LOSF. Explain mean reversion and calculate a mean reverting level. We've explained mean reversion. Let's calculate the level now. Assume that changes in the civilian unemployment rate are covariant stationary, and that an AR1 model is a good description for the time series of changes in the unemployment rate. So it is covariant stationary, and we know that all covariant stationary time series will have a mean reverting level. And we're told the AR1 model is a good description, so we're going to have a mean reverting level. Specifically, we have the change, or first difference in the unemployment rate, is equal to negative 0.0405 minus 0.4675 4 times the lagged first difference. Okay, given this equation, what is the mean reverting level to which changes in the unemployment rate converge? And we can do this two ways. We can use B naught over 1 minus B, and we know what B naught is. It's 0.0405, negative 0.0405. We know what B1 is. It's 0.4674. It's 1 minus, since that's a negative, 1 minus negative 0.4 is 1 plus 0.4. That's why we get 1.4674. So we could just calculate it this way, or we can say at a mean reverting level, the first difference at time period t will equal the first difference at time period t minus 1. And we know that UERT equals all of this up here. And since UERT will equal UERT minus 1, for UERT minus 1, we'll just substitute in UERT. Isolate, solve, we get negative 0.0276. When I say isolate and solve, all you're doing is just bring this over to the other side and using algebra. Notice what we get over here. 0.0405, well, there's B naught. Over 1.467, well, there's 1 minus B1, because, of course, it's negative, right? So if you just use this equality and say, okay, well, let's just isolate terms over here. Let's do some algebra and isolate the difference, UERT over here. You will get this. You will notice that this is the same as this over here. So you can go about it both ways. And we get negative 0.0276. So the mean reverting level for this AR1 model is negative 0.0276. So when the first difference is negative 0.0276, it will predict that the next value of the difference will be negative 0.0276. All right, question 7 just sort of combines mean reversion with forecasting several periods ahead here. Suppose the following model describes changes in the civilian unemployment rate, and this is the model we just had in the last question. The current change, or the first difference, in unemployment rate is 0.0300. Assume that the mean reverting level for changes in the unemployment rate is negative 0.0276. We already figured that out. A, what is the best prediction of the next change? Well, that is easy. If this is our formulation, what is the prediction of the next change? We just substitute 0.03 in for the current first difference, and that will give us a forecast of what it is next period. Here we're using UERT minus 1, and that is the same thing as saying UERT plus 1 equals B naught plus B1, and the change in UERT. We're told that UERT is 0.0300. We're being asked to find the prediction, the next change, which is T plus 1. So we just substitute it in. We get negative 5.45%. B, what is the prediction of the change following the next change? So we need UERT. I put T plus 1 here, but you could also write T plus 2, because that is what we're doing, T plus 2. I was just going from T to T plus 1, but if we went from T plus 1, this would be T plus 2. And it's the same formulation, except in here we put the value that we arrived at for our forecast. So we don't know what the actual first difference is. We know what the forecast will be. We're using the forecast in here, and that'll get us to 0.0150276. Now, is any of this making any sense? Well, remember, we had a mean reversion level of negative 0.0276. So any first difference above it will tend to pull it down. Any first difference below it will tend to pull it up. So we had 0.0300, which is above the mean reverting level. So we should have got a forecast that is pulled towards, that is pulled down from 0.0300, and we get negative 5.45. So it was pulled down. Negative 5.45 is below the mean reverting level, so it should predict something that pulls the value up, and it pulls it to negative 0.01502, which is somewhere up here. So we did this. So notice that we are being pulled towards the mean each time. C, explain your answer to part B in terms of equilibrium. Well, we just did that. We just did that and noticed that we've gotten a little closer to the mean reverting level each time. Now, just because we have a mean reverting level does not mean that this will happen. That's not what that's saying. And what it's saying is that over time it will get pulled back. That does not mean in the very next period either. This span of time here could span 4, 5, 6, 7 periods. It could be a couple of years before it finally gets back there. It depends on the strength of that mean reversion. So all mean reversion is telling us is that once we start moving away below the mean reversion level, there is a force that's pulling us back. But that does not mean we're going to stop right there. A mean reversion level doesn't mean we find this point and then that's it and it's over. It just means that there's that tendency that's in there. Well, we're looking at question 8 now, and question 8 asks us to go back a little bit in the learning objectives. I think we're at the LOS-D. Describe the structure of an autoregressive model of order P. We've done that. And calculate 1 and 2 period ahead forecasts given the estimated coefficients. So let's go ahead and do that. What do we have here? Table 3 gives the actual sales, log of sales, and change in the log of sales of Cisco Systems for the period Q1 2001 to Q4 2001. So what do we have? We have actual sales, this is the log of sales, and then this is the change in the log of sales. So from this period to this period, that's the change from 87825 to 8817. That's the difference. These are first differences here. Forecast the first and second quarter sales of Cisco Systems for 2002 using the regression. Now it's asking us to forecast the sales. So it wants these numbers in here using the regression as follows, which I've rewritten here in blue. So let's go ahead and do that. Now the first thing we need to calculate are our differences here. From our differences we can get the log of sales, and from log of sales we can get the actual sales. So Q1, the change in the difference for log of sales, t plus 1, we'll use the t value. So we need this t value here because, let's just calculate here. This is t plus 1, this is t plus 2. So to forecast anything here, we need the value before, 0.0954. We calculate and we'll get 0.02128. And to go t plus 2, we just take the value that we arrived at here, and that gets plugged in to here. Because we're getting t plus 2, we'll need t plus 1, and that gives us 0.076097. There we go. So 8.3659 plus this number will give us this value here, 8.3659 plus the difference that we've just calculated. Gives us 8.38718, and 8.38718 plus the next difference will give us this value, 8.38718 plus the next difference that we calculated for t plus 2, 8.463277. Well, if this is the log of sales, to get sales, all we do is we raise that to e to the power of that value. So e to the power of 8.38718 gives us 4,390,419. Since this is already in millions, we can take off the last 6 digits here. We get 4,390, and here we just raise e to the power of this value, gives us 4,737. So I think that's fairly easy. All we did was we just forecasted the period ahead, the t plus 1 change in log of sales by using the lagged value. And to calculate t plus 2, we didn't have a lagged value, so instead we used the predicted value that we got instead. So if we look at the how much faith we have in our forecasts going forward, we would have more faith in Q1 2002 being closer to reality than we would have for Q2 2002. And if we can continue on now, well, we can certainly continue on because we can calculate the next change in log sales because we have t plus 2. So we can easily go to t plus 3, t plus 4, t plus 5, calculate the differences, add the difference to the log of sales, raise the log of sales up at the power of E and calculate the actual sales. But again, the further out you go, the more inaccurate those forecasts become. So you might not want to go out more than 4 quarters. And at the end of the first quarter, once Cisco reports earnings, you would update the value, the difference in here, and perhaps it's in a spreadsheet or something where once you re-enter this value, it cascades down and changes all of your forecasts dynamically for you, however you want to model that. But there we go. We've satisfied that learning objective. I think you should be able to replicate that if you see it again. Just a few more loose ends to tie up in section 4 before we move on to random walks. Comparing model forecast performance. And when we're comparing forecast performance, remember we make a distinction between prediction and forecast. Prediction means we're using the model to predict what the in-sample value should be, and then we can look at the deviations from that. Forecasting means out of sample, right? So for in sample, we can look at the variance of the error terms of model 1 versus the variance of the error terms of model 2. And clearly, the model with the smaller variance in the error terms is the more accurate one. I think that makes a lot of sense. That is an in-sample. That's when we're dealing with in-sample forecast errors. Predicted versus observed values used to generate the model. Out-of-sample forecast errors, we compare the forecasts that our model makes versus the outside the model values. And here we will calculate something called a root mean squared error, RMSE. And you can have your statistical package output an RMSE as well. It's used to compare out-of-sample forecasting performance. So it looks like this. What do we have here? Let's break it down. This is basically the square root of the average squared error. That sounds kind of confusing, right? It's like my brother's uncle's sister's nephew. The square root of the average squared error. Well, let's look at it. What do we have in the numerator here? This is the actual observed value minus the forecast. So this is the error. Here is the squared error. Divided by n is the number of observations we're going to make. So this is the average squared error. And this is the square root of the average squared error. So it doesn't look that bad when you look at it that way, right? The smaller the RMSE, the more accurate the forecast. And finally, we'll discuss something called the instability of the regression coefficients. And this has to do really with our selection of the time period in which we select our time series from. Regression coefficients can vary based on different sample periods. For instance, if we're looking at period of 1965 to 1975 for some economic data versus 1985 to 1995, so a 10-year period. But we're going to get different regression coefficients during this period of time than we would during this period of time, simply because we had different economic regimes at that point in time. So we're going to see different values for the regression coefficients. And regression coefficients can vary based on the different time periods. Let's say we took a time period of 5 years and observed a variable and did a model, an AR1 model, let's say, and looked at the coefficients versus maybe 8 years or 10 years or 12 or 3 or 2. You might have different regression coefficients at that time. That's why we talk about the instability of regression coefficients. They will vary based on the sample period and based on the amount of time within the sample period. The choice of the model may also change depending on the time period choice. So 65 to 75 may be well described by an AR1 model, but 85 to 95 might be an AR2 or an AR3. So there's a lot to think about. So how do we choose the time period? How do we choose the length of the time period? Experience and judgment will help decide the correct time period and thus the correct model. So if we're looking at something, and let's take a look at something that I did for my PhD. I looked at the pattern of patent citations for the period 1972 to 1992, a 20-year period. And I wanted to look at where the top 1% of the most highly cited patents came from, whether it, what sector of the economy it came from, and whether it came in expansions or recessions. The problem was a lot of the patent laws changed right around 1982. Previous to 1982, government-sponsored university research, unfortunately, the patent belonged to the government. After 1982, the researcher themselves could own the patent on the on government-sponsored basic research. So there were two very distinct periods, pre-82 and post-82. So after I ran the full series, I had to say, well, you know what? I really have two different series here. I need two different models, models to model what I was looking at. So again, that's experience and judgment. You just have to know. Well, look, I'm modeling this particular economic series. I know that this particular event happened at a point in time that changed things, and that's basically how it works. Let's underline those words again. Experience and judgment will help you decide on the correct time period. All right, well, I thought it might be useful right now to go through example 6 and follow this story through the next few examples and show how model development can change, and how when we develop a model, the big question is, well, how do we know what model to develop? And the usual answer is let the data tell you. So we're going to see how the data informs us on how to progress here. So here we go. Analyst Lisette Miller has been directed to build a time series model for U.S. monthly inflation. Inflation and expectations about inflation, of course, have a significant effect on bond returns. For a 30-year period beginning with January 84 and ending with December 2013, she selects as data the annualized monthly percentage change in the CPI. Which model should Miller use? So we're going to go through two issues here. Number one is, what model is appropriate for this time period? And the second question then becomes, is a 30-year period an appropriate time period for what she wants to do? Clearly, she wants to forecast ahead of time. Is 30 years the right model, the right time frame to use? So we'll have a look at that as we continue on. So here we go. What's the first model? An AR1. She's estimating an AR1 model. Inflation at time t is B0 plus B1. Inflation at time t minus 1. Okay, so let's just go right to our model. When we're doing something like this, an AR1 model or any AR model, you can skip all of this stuff up top. There's no point in going through it until you look at the autocorrelations of the residual down here. You got to look at this, because if you cannot accept that the model has no autocorrelation, you can't continue. So let's have a look at our T statistics. 1.7, that looks fine for a lag of 1. But 2 lags back, we have correlated errors. 3 lags back, 2.97, that's going to be significant. We have correlated errors there, but not 4. So 1 and 4 is okay, but 2 and 3. Doesn't matter. We still have correlated errors here. At 2 lags back, we have correlation. At 3 lags back, we have correlation. None of this matters anymore. So at this point, we have serial correlation. There's no point in interpreting the results. We need another model. So what do? Is we scroll down here. If she estimates the equation with 2 lags, inflation time t is B0 plus B1. There's our first leg, plus B2. There's our second leg. So here's the results from going from an AR1. Now remember, we started with AR1. We had serial correlation, which means if we had a distinct independent and dependent variables, serial correlation would tell us we have a missing variable. So we do the same thing here. We say, well, we got serial correlation. We have a missing variable. The only variable we have is time, so let's stick in another lag. And that's how we get to the second leg. So there's our intercept. There's our first leg, our second leg here. Let's have a look at our T statistics for our autocorrelations. They all look insignificant. In other words, we will not reject the null hypotheses that these are equal to 0, because that is the null, that all these are equal to 0. We accept that they're all equal to 0 at this point. We fail to reject, so we'll accept the fact that these are all equal to 0. We have no serial correlation. This is the specified model. This intercept and 2 lags become the specified model. And if we look, we have an intercept that is significant. We have a first coefficient on inflation on the first leg that is significant. And we have a negative coefficient on the third leg that is significant as well. The model R squared is 0.23, standard error 3.36, 358 observations. And what do we do with this? We ignore it. It's useless in an AR model. All right, let's move on to part 3 of our story here. Part 1 was the AR1 model. Part 2 was going on to the AR2 model. Part 3 is saying, okay, well, let's do some forecasting on this, and let's evaluate the performance of these 2 models. We normally wouldn't use the AR1 model in a forecast to determine whether it's better than the AR2 model, because we looked at the AR1 model, had serially correlated errors. We know that the coefficients are meaningless at that point. All of it is meaningless. We can just ignore it. So we wouldn't actually use it, but just for exposition purposes, just to show you the difference in the RMSE between the two, we will. So here's what we're going to do on this one here. Our data series, our time series ended at 2013. We're going to go to January 2014 to September 2014, and we're going to look at the observed inflation rate at that point in time. Here's our first lag and our second lag. We're just putting them in order, and you can see that we have a lag here. There's March at 8.0077. So when we go to April, the first lag should be March's value. When we go to May, the second lag should be March's value, and you can see that they line up. Using the AR1 model, we calculate a value and we compare it to the observed value. We have a predicted value compared to the observed value. There's the error. There's the squared error, and we just do that for all of them. There's the squared error. So we take the sum of the squared errors, we divide by n, we'll get the average, and then you take the square root of that, will give us RMSE 2.4396. And we'll do the same for the second model. This is the error derived from the second model. Here's the squared error from that model, and we have an RMSE of 0.3498. And not surprisingly, the AR2 model is more accurate than the AR1 model, 2.4396 versus 2.3498. This example really just shows us the process we would go through to compare two models. You certainly would not compare a discarded model with an accepted model. We've discarded the AR1 model previously. We would not judge how well it forecasts going forward, because we know that we have a problem with the coefficients. So we wouldn't use it. That it's being used here is not an example of how you would use that model. It's just an example of if you were going to compare two models. Let's just suspend disbelief right now and just say, you know what? The AR model was good enough. And this is how you would compare the fit between two competing models. Let's go to the final part of this story here. Instability in time series models. And let's just do some reading, and it should be no surprise what we get to here. In example 6, analyst Lisette Miller concluded that U.S. CPI inflation should be modeled as an AR2 time series. A colleague examined her results and questioned estimating one time series model for inflation in the United States since '84, given that the Federal Reserve responded aggressively to the financial crisis that emerged in 2007. He argues that the inflation time series from '84 to 2013 has two regimes, or underlying models generating the time series, one running from '84 to 2006 and another starting in 2007. Therefore, the colleague suggests that Miller estimate a new time series model for U.S. inflation starting in 2007. Because of his suggestion, Miller first estimates an AR1 model for inflation using data for a shorter sample period from 2007 to 2013. So, she's taking her 30 years and saying, okay, well, maybe you got a point there. Let's find out. So, she takes the new time series from 2007 onwards, and once you do that, once you go from your 30 years to a different time series, you cannot just bring your AR2 model forward and say, well, we're going to use the AR2 in this one. You start over again at an AR1, because it may be the appropriate model at that point. So that's what she does. She runs an AR1 model on that new series. Let's just run right to the autocorrelations. Look at that. They're all fine. An AR1 model describes that data just fine. We don't need the AR2 model for this particular time series. The AR1 model does just fine. We have a questionable intercept. The intercept may be 0 because 1.79 may not be significant, but the inflation, the slope intercept, the slope coefficient, the B1 coefficient, does appear quite significant at this point in time. So let's have a look at what the data looked like for the first 30 years and see if if we looked at this particular chart before we even ran the model. Let's say we had our 30 years of inflation and we graphed it out. Would this graph signal to us that 30 years is probably not appropriate? Well, it kind of looks like we have a constant mean, but do we have a constant variance? It seems that this is nice and tight along here, but then it kind of explodes out right around 2000, 2002. And this is pretty much when China entered the World Trade Organization, WTO, I think it was 99, 2000. You can start to see the inflation widening out in this. Now, the analyst was saying up to 2006 it looked like one regime, and after 2007 it looked like another. I would look at this and I would say, it appears to me that after about 2002, we have a different type of regime than we did before. In fact, I'd almost say the cutoff would be 1999. That's when we started getting a lot more. Look over here. You hardly have anything below the zero line, but look at what's going on here. You have much higher peaks and valleys in the change, in the period over period changes. So I would have said, looking at this initially, I probably would not have gone with the policy decision of saying, well, you know what, policy changed around 2007. I would have let the chart allow me to choose what I wanted. And I would have said, well, somewhere around here, when I start seeing all of these drives down below the zero line, I'd probably make a cutoff around 2002, 2001, and use this as one time series and that as another time series. What I would probably be interested in doing at this point, being that there is a policy change in 2007, is running 2007 to 2013, then running 2001, let's say, to 2013, and seeing if an AR1 model does fit that, and then comparing those two on their RMSE. I think that would give each one a run for the money. That would be interesting to see which one would win, because it's not clear which one would at this point. But that's what you would do as an analyst. You'd look at the data and you'd say, well, what do I see going on in here? I see more here. You'd use the chart, which would tell you, or the graph, I should say, which would tell you that there is differences. And then you'd also use the fact that, well, policy did change. So you'd want to run a bunch of different models, and you'd want to choose the one that forecasted better. You're not trying to find the one that fits the data better. You're trying to find the one that would forecast the next 6 or 7 or 8 months better. That's the one you want to use. Well, let's have a look at question 9. What do we have here? Table 4 gives the actual change in the log of sales of Cisco Systems from Q1 2001 to Q4 2001. So what do we have? Actual values of the changes in the log of sales. There we are. This is the forecast value. All right. Along with the forecast from the regression model, change in the log of sales equals, that should be an equal sign. Let me put another line in there, equals 0.0661 plus 0.4698 change in the lagged variable of sales. Estimated using data from Q3 91 to Q4 2002. Note that the observations after the fourth quarter of 2000 are out of sample. Okay, so these are out of sample, we know that. A, calculate the RMSE for the out of sample forecast errors. So the RMSE we know is the actual value minus the forecast. And we're going to square that and find the average of that, then take the square root. So it's the root of the mean of the squared errors. The root of the mean of the squared errors. That's how you can remember it. It's just RMSE, right? So here's our actual. All our values here are our actual values minus our observed values, or sorry, our forecast values. We're going to square them, and we're going to add them up. We get 0.29113, divide by 4, because we have 4 of them, and we get 0.0727. That's what's inside the root. So the numerator is this value here. The denominator, n, is 4. This whole term in here is 0.0727. Once we take the square root of it, we get 0.269811. There's your RMSE. Nice and simple. No point in me going through all of this. This is all really just calculator work. We just want to see the actual process of the steps we go through. B, compare the forecasting performance of the model given with that of another model having an out-of-sample RMSE of 20%. So 20% versus, what do we have? 0.2698, 26.98%. The lower the RMSE, the better it is. 20% versus 26.9%. And what is an RMSE, right? It's the error. It's the root of the mean squared error. So obviously the lower our errors are, the better it is. 20% versus 26, we'll take the model that has an out-of-sample RMSE of 20%. All right, let's have a look at question 10. A, the AR1 model for the civilian unemployment rate, which is here, and we've seen this in a number of previous examples, was developed with 5 years of data. What would be the drawback to using the AR1 model to predict changes in the civilian unemployment rate 12 months or more ahead as compared with 1 month? Well, I think right away we can see the further out you go, the less accurate it becomes, right? Number one, loss of accuracy as T plus K increases. Capital T representing the end of our time series, our time period of which we have data, and K being the number of periods out from the end of the period that we have, the number of periods into the out of sample period. You'll also recall that our mean reverting level, B0 over 1 minus B1, was negative 0.0276. So this is a mean reverting level in the change, in the period over period change. Well, it's negative. So you'd be facing the prospect of continued decreases in the civilian unemployment rate, and we know that can't happen. Most advanced countries have an unemployment rate, a maximum minimum unemployment rate of around 4%. That would be maximum employment rate, only because there's a certain amount of voluntary unemployment or frictional unemployment that happens all the time. Only communist countries claim 100% employment rate, which we know is not true. The second problem is representativeness. As you're saying, well, we're taking the last 5 years. If you're going to go out another 12 months, you're suggesting that the model you have is going to represent what the next 12 months are going to be. Perhaps it will not be representative. B, for purposes of estimating a predictive equation, what would be the drawback to using 30 years of civilian unemployment data rather than only 5? Well, we saw this in the example of Lisette Miller calculating the inflation rate in example 6 that we looked at. She used 30 years of data, and it appeared to capture 2 separate regimes. Well, if we're going to go 30 years on unemployment is very, very tied to the business cycle. You have multiple business cycles over those last 30 years. You're going to have multiple regimes. So it's going to capture more than just one regime. It captures multiple business cycles, maybe more than one series in there. So it's going to be non-stationary. Even if you take first differences across all those 30 years, if you have 2 separate series in there, even after taking first differences, those first differences will still show 2 separate series. It's non-stationary. Even with first differences, it will be non-stationary. So this is that's a good example of, especially something like unemployment that's tied so tightly to the business cycle. Taking a 30-year period simply is just not the appropriate thing to do given that data. All right, we're ready to talk about random walks and unit roots. But just to set the stage for the random walk, you'll recall at the beginning of the video series, I talked about time series in terms of 4 things that we want to look at. The trend, cyclicality, seasonality, which we will get to, and a random component. Well, let's imagine for a moment that we look at a time series and there is no trend, there is no cycle, there is no seasonality. It is nothing but random, just random movement. Take a coin, heads or tails, and flip it. And every time you flip it, if it's heads, you'll mark a tick up on a graph. If it's tails, you'll mark a tick down. You'll draw out what looks like a stock price chart. It will look like a stock chart. But we know that that was completely generated by a random process. Now, if I said to somebody, here's a time series of data, what do you see here? You could not extract a trend from it or any cycle or any seasonality. It is purely just random. So are there time series data in finance that is nothing more than just randomness? And the answer is yeah. There's quite a few series that a lot of practitioners would say that if you try to model it, you'll get nothing but a random component. There is no trend, there is no seasonality, there's nothing there but a random component. The random component takes everything. That's called a random walk. So let's have a look at what a random walk would mean. And a random walk is a special condition of an autoregressive series, an A1 series. Imagine an AR1 formulation where B0 equals 0 and B1 equals 1. That is called a unit root. When the slope coefficient is equal to 1, it's called a unit root. When it is equal to 1, it will have no mean reverting level. For an AR1 function to have a mean reverting level, the coefficient, the B1 coefficient, the absolute value must be less than 1. So let's write that out. Well, xt would equal, well, since b naught is 0, we wouldn't put b naught. It would be b naught plus b1 xt minus 1. b naught is 0, we can drop that out. b1 is 1, so you could just drop that. xt, the value of x in time period t, would equal the value of x in the prior period plus some error term. So that the value in xt2 would equal the value in the previous period plus some error term. So we can see that the cumulative effect of xt is just the sum of all the error terms from period to period, because it would equal itself plus some error term. The next period, it would equal itself plus some error terms. So the error terms would accumulate, and that would draw out the chart. The error terms explain the entire chart, or explain the entire time series. In other words, the entire time series is explained by a random component. The value of the series in one time period is the value of the series in the previous time period plus a random error, an unpredictable random error. And we can kind of tell when we have a time series as such. If we look at the errors, the expected value of the errors will be 0. They're unpredictable. The expected value is 0. The variance, the error term in every time period will have a constant variance. In every single time period will have a constant variance. And the error terms are uncorrelated across time. Now think about this last statement, the error terms are uncorrelated across time. Well, that's the very definition of a random walk. Because if the error term showed any correlation whatsoever, that means the error term is picking up a relationship that we have not modeled, if they're correlated, correct? Which means we don't have a random walk. So if the error terms are uncorrelated, and the error terms have all of the explanation, and they're uncorrelated, that means there's nothing left to explain any movement. It is purely just a random walk. Random walks have no finite mean reverting level. We calculate the mean reverting level by b naught divided by 1 minus b1. Well, if they're both 0, you'll get 0 over, they're not both 0. b naught is 0, b1 is 1. You'll get 0 over 1 minus 1, which is 0, 0 over 0. That's undefined. And it has no finite variance, because at each step along the way, it picks up the sum of all the error terms. So xt, the value at xt, will be the value previous to it plus its error term, which xt will equal xt plus 1 plus the error term. xt plus 1 we get from xt minus 2 plus the error term at t minus 1 plus the error term at t, and on and on and on until we get all the way to time 0 is just the sum of all of the error terms. So the variance actually ends up exploding. It's t minus 1 times the variance. So you may have a constant variance at each time period, but the variances are additive. So let me see if I can show you what I mean using two graphs, two charts here to kind of show you. Let's take a series that is mean reverting and has a finite variance. We know it kind of looks like this, right? So if we were going to look at it in terms of a normal distribution, there's our mean, we can see that it has finite variance. But if we take a random walk, we don't know where it's going to head to. So let's just stop there. It has no mean, it has an undefined mean, but if we were going to take a distribution, again, we can't really because it has no mean, but let's just say we were, it would look like that. All right, so let me just show you something now. Keep that in your mind. Let's just keep going with this random walk. And we'll just keep going. Now, if we were going to look at it, look what happens. The distribution is wider to cover off the highs and the lows, the variation in what we're doing. We still can't say that we have a mean. This is, again, I really should not be drawing this to show you. I'm really just showing you that the variation is the sum of all of the error terms as we go on. Here, the sum of all the error terms is not additive. They're all independent. But here they are not. They're additive. So you have a variance that continues to explode. Because of that, We do not have covariance stationarity. It is not covariance stationary, so you cannot calculate an AR model. You must make it covariance stationary first. And yes, even with a random walk, there is a way to turn it into a covariance stationary model. You cannot estimate an AR1 on a time series that is a random walk. So that brings up the question of, you got two questions here. We'll answer the first one. If you cannot estimate AR1 on a time series that's a random walk, can you do something to make it stationary? Yes, you can, and I'll show you. And before we do all of that work, is there any way to find out if a time series has a unit root before we start? Because if it has a unit root, then we know that we can take care of it by doing some things. And if it doesn't have a unit root, maybe we don't have to do anything. Is there any way to find out before we start the process? Yes, there is. And this the strategy we would use to turn it into a covariant stationary time series, we've already seen is just first differencing. Is we create a new series, which is just delta xt, is just the first difference in the variables. We take the observation at time period t and we subtract from it the observation at time period t minus 1. And it's just the difference between the time periods, called first differencing. Transforms a non-covariant stationary time series to a covariance stationary time series, even a random walk. So here, note that the delta xt is just the difference, which is just the error term. It's just going to be the error term. If we're taking xt and subtracting xt minus 1, all we're left with is the error term. And since the expected value of the error term is 0, the expected value of the difference will also be 0. So once we do a first difference on a random walk, remember a random walk had a b0 equal to 0 and a unit root. Once we do first differences, we should expect to find a b0 still equal to 0, but b1 will now be 0. Why? Look, the expected value of the difference is 0, which means our coefficient must be 0. But now we have a mean reverting level. b0 over 1 minus b1 was still 0. We have a mean reverting level of 0. And the variance of the change of the first difference is just the variance of the error term for all t. It is not additive. It's not additive. Why? Because we have a mean reverting level. So it's not additive. We can now use regression. However, here's the problem. No forecasting power, however, since b0 and b1 is equal to 0. So you're thinking, well, what's the point? What's the point of doing a first differencing on a time series to make it stationary just to find out that it's a random walk? That's the point. We can only conclude that we have a random walk. We have nothing. So, for instance, the textbook gives an example of currencies. And that a lot of research has shown that if you model currencies, if you make a currency covariant stationary and model it, you get nothing but a random walk. Well, that's powerful enough in itself. To know that something is a random walk means that by its very nature, you're not going to be able to forecast something that is almost 100% unpredictable, like a random walk, like a currency movements. So if we can't forecast, if we can't model, we can't reduce uncertainty, all we can do is get out of the way or hedge, right? So knowing that something is a random walk is a powerful statement in itself. Now, I brought up the idea of the currency being a random walk. And do I believe that a currency is a random walk? Yes and no. Yes and no. Having been a currency trader, I can tell you that, well, you know what? Over long periods of time, yes, it is a random walk. If you're asking me where it's going to be in 4 or 5 years, I haven't got a clue. I mean, I really haven't got a clue. If you ask me where the stock market, where the S&P 500 is going to be in 20 years, higher. That I know, higher. It'll be higher. That's easy. That one's easy. Where's it going to be in 10 years? Higher. Where's the currency going to be? Who knows? But over short periods of time, it is still a random walk, but I do know, or at least I have some feeling based on certain other fundamental things, certain economic data, monetary policy, etc., whether or not the currency is going to drift upwards or downwards. But it's still a random walk. The random component is still the big thing in it, but there is some direction. Hence we have things that are called random walk with drift. Any currency trader will tell you, look, over short periods of time, based on statements from a central bank, whether it's going to be in a tightening cycle or a looser monetary policy, we sort of have an idea of where the general trend of the currency will go in relation to another one over a period of time. So we can't say it's truly a random walk. There is some nudging in there. Hence, we can model it as a random walk with drift. It's still a random walk, but when we have drift now, we still have a unit root, but our beta naught, our intercept coefficient, is not equal to 0. That's the drift component. So after first differencing, because you can't, if it is a true random walk, you have to difference it first to make it covariant stationary. After first differencing, we look at our AR1 model. We should have an AR1 model with beta naught not equal to 0, and beta 1 will be equal to 0 at that point. After first differencing, it will be equal to 0. So what are you going to get? Your first difference, your change in xt. Remember, with just the random walk, the change in xt was equal just to the error term. Now it's equal to b naught plus the error term. So it's equal to the random component plus the drift component. The drift component is b naught. In other words, we expect period over period the value of xt to change by some constant amount plus a random term. That is the drift. That's what will drift it either upwards or downwards, because it'll keep adding on. And this random component, the random component may be doing this. But if we're adding a constant amount to it each time, it'll become additive. It'll start raising this to start drifting like that. There's the drift component that we're looking for. Still not a trend. The trend relates to B1. That is 0. Still no trend. It's a drift in a random walk. So there's what a random walk would look like. So how do we know, before we even begin with an AR1 model, let's say that we're ready, we're sitting there, we're saying, okay, let's run an AR1 model, and your partner nudges you with his elbow and says, you should run a test first to see if we have a unit root. How would you do that? Well, there is a unit root test of non-stationarity. It's called the Dickey-Fuller test for a unit root. If a series is covariance stationary, then the absolute value of the B1 term will be less than 1 from an AR1 model. So if it is covariant stationary, that will be a fact. Let's remember that now, because we're going to build into this test. That will be a fact. I think we get that. If the coefficient is equal to 1, then the time series has a unit root, because it is equal to 1. That's the definition of a unit root. It is a random walk. If it has a unit root, it is a random walk. It is not covariant stationary. So how are we going to test this thing? We can't just run an AR1 model, look at B1, and if B1 equals 1, look at the test statistic. Is it significant? Then yes, B1 equals 1, there we go. Because if B1 does equal 1, we have a random walk. It is not covariant stationary. You cannot trust the output from an AR1 model anyways. So you can't go down that road. So you cannot test B1 from an AR1 model. So here's what the Dickey-Fuller test does. They took the original AR1 model, xt equals b naught plus b1 xt minus 1. We have a lagged variable of the dependent variable and the error term. And they said, let's just subtract xt minus 1 from both sides. So xt minus 1, what is that going to give us? That's going to give us a first difference. We'll end up with a first difference on this side, equals b naught plus b1 xt minus 1 plus the error term minus the xt minus 1. So we're subtracting it from both sides. Collect terms, because you have b1 xt1 over here, and this is, you can put a 1 in front of it, 1. So we have b1 minus 1 xt minus 1, and we're going to call this g. So what are we doing? We have first differences, and here we have first lag. So it's a regression of the first differences and the first lag. And we'll get a value for g. Well, g we know is equal to b minus 1. So what are we going to test? Dickey-Fuller tests the null that g equals 0. If they fail to reject the null, then g equals 0. Well, how do you get g equaling to 0? What must b1 be for g to equal 0? b1 must be 1. So by doing this, we turn it into a covariant stationary time series, and testing g equal to 0 is the same as testing b1 equal to 1. Kind of ingenious, isn't it? So we test that g equals 0. The alternative is g is less than 0. It would have to be less than 0. So if we can reject the null, we accept the alternative, we do not have a random walk, off we go. If we cannot reject the null, we have a random walk. Now, you cannot use, this will give us, the Dickey-Fuller test will give us a t-statistic. We have to compare it against a critical value. You cannot use the normal t-critical values. Dickey-Fuller's computed a whole bunch of t-statistics for this test that are larger than the conventional t-values. So you'd have to have a separate table for that. But here's the thing. You're not going to do this on your own. There's no way you're going to do this. You're going to have some software package do it for you. You have to recognize that, hey, I want the results from a Dickey-Fuller test, and I want to be able to interpret the results. So you want to know the test you're looking for. You want to know what you're testing for. You're testing for a unit root. You want to know that you're okay to reject the null and accept the alternative, which means we do not have a unit root, which means we have a covariant stationary model that I can now use to forecast and say something. There is some trend and some cycle in here that I can pull out. It's not just pure random. So I thought it would be good to go through example 10 that's in your book, because this shows us the process that we would go through. Well, not so much the process we would go through, but you know, the kind of paradoxical results that we would get. This is the yen-US dollar exchange rate example. It's a pretty good one. Financial analysts often assume that exchange rates are random walks. Consider an AR1 model for the Japanese yen-US dollar exchange rate. Table 9 shows the results of estimating the model using month-end observations from January 80 through December 13. Now, when you're doing really long series like this on currencies, yeah, I would bet almost 100% that every single one you're going to do is going to be a random walk over long periods of time. But if this were over a short period of time, let's say from 2012 to 2016, when the central bank decided to intervene heavily and the government decided to intervene heavily in pushing the value of the yen down, no one would argue that there was no drift there. There was. But anyways, this is a long period of time. We should find a random walk. So here's the results from a regression. And we didn't, notice here, we're just using a lagged variable. So we're just using last month's exchange rate at that period of time to predict the next period's exchange rate. We're not differencing. We're just using a standard AR1 lagged model here. So let's look at our autocorrelations. Notice none of them are, we can say, look, we have no autocorrelation here. They all look like they would, we would fail we would reject the null of these being any, or fail to reject the null of these being any different from 0. We have a t-statistic on the intercept that looks like we would reject, fail to reject the null as well. So we could say that the intercept is 0. And we have a highly significant t-statistic, but look at this, it's 0.9903. That's basically 1, so it looks like we have a unit root. So on this case, you would say, well, it looks like we have a unit root. Here's the problem. If we do have a unit root, this is a non-covariant stationary series, which means you cannot even trust the output from this. So let's just continue down here and see what we did. So to get it to be covariant stationary, they took first differences. So now our variable is the first difference. Well, we're going to predict the first difference by a lagged first difference. So let's look at our autocorrelations of the residual. Again, none of them are significant. Doesn't look like we have any autocorrelation going on. And let's look at what we have here. For our t-statistic, not significant, which means our intercept and our B0 coefficient and our B1 coefficient are no different than 0. So what is we can't accept these coefficients. So if we were going to write out our formulation for this AR1 model, what would it be? It would be the difference at time t is equal to 0 plus 0 times the difference at time t minus 1 plus the error term. Well, all the zeros cancel out and all you get is the error term. Here you have a true random walk. How did we determine that? We ran the regression on first differences, an autoregressive regression on first differences. We made sure we had no serial correlation. We noticed our t-statistics, none of them are significant, which means none of these are any different than 0. Well, the Dickey-Fuller test just allows us to test it right up front without going through all of that. So I think example 11 is really interesting, and it highlights the process, the thinking that you would go through when you're first given an assignment to do something, how you would proceed from zero. Okay, I give you a time series, I say, okay, go, and the steps that you would go through, even though it's very, very short. There's a lot packed in here, and I want to draw your attention to the important points here. So let's just read along. In January 2012, equity analyst Aaron Berglund is building a time series model for the quarterly sales of AstraZeneca, a British-Swedish biopharmaceutical, that's a lot of terminology in there, biopharmaceutical, right? Company headquartered in London, UK. He's using AstraZeneca's quarterly sales in US dollars during January 2000 to December 2011 and any lagged sales data he may need prior to 2000 to build his model. He finds that a log linear trend model seems better suited for modeling AstraZeneca's sales than does a linear trend model. And I think we could have seen that pretty much right away if you're modeling raw sales numbers. There's going to be a growth factor to sales, not a constant amount to sales per period. However, the Durbin-Watson statistic from the log linear regression is just 0.7064. Which causes him to reject the hypotheses that the errors in the regression are serially uncorrelated. He concludes that he cannot model the log of AstraZeneca's quarterly sales using only a time trend line. He decides to model the log of AstraZeneca's quarterly sales using an AR1 model. He uses the natural log of the log of sales plus B0 plus B1, and of course the lagged log. So he's going to keep it in log form, which you would. But he's using a lagged variable now, which is an AR1 model. So remember at the very beginning, I said, here's the process we'll go through. We'll test for a linear relationship, a linear trend. Here he found that he couldn't use a linear trend. He used a log linear trend. Used a log linear trend, found that he had serially correlated error, says, well, I can't use that. So let me now move on to the AR model, the autoregressive model, and I'll use a lagged variable. So now he's using this. Here's the important point. Notice the process he went through. Watch what happens now. Before he estimates this regression, he's decided he's going to use an AR1. Stop. Before he estimates this regression, the analyst should use the Dickey-Fuller test to determine whether there is a unit root in the log of AstraZeneca's quarterly sales. If there is a unit root, there's no point in going any further because it is purely just random noise at that point. You're not going to find anything. If he uses the sample of quarterly data on AstraZeneca's sales from the first quarter of 2000 through to the fourth quarter of 2011, takes a natural log of each observation, and computes the Dickey-Fuller t-test statistic, the value of that statistic might cause him to fail to reject the null hypotheses that there is a unit root in the log of AstraZeneca's quarterly sales, in which case he'll say there's no point in modeling this. It is purely just a random walk. It's going to have no forecastability. So what good is a model if I can't forecast with it? I don't need it to explain what happened. I can just look and see what happened. I don't need it to explain. But if I can build a model that can explain what happened and have forecast ability, great. But with a random walk, there is no forecastability. What's the point? So I think that's a pretty good example of the process that you would go to. Let's continue on with example 12. I know I'm taking a lot from the book here, but a lot of the learning here really happens in the examples because they're quite good. The plot of the log of AstraZeneca's quarterly sales is shown in Figure 10. So let's anytime we get to something, I always say take a moment and look at what it is that you're given. What do we have on the vertical? We have the natural log of sales in millions, and across the bottom we have a year. By looking at the plot, Berglund is convinced that the log of quarterly sales is not covariant stationary. That is, it has a unit root. Well, of course, look at it. It's moving in one direction. If it were covariant stationary, it would tend to have some mean reverting level. This does not look like it has a mean reverting level. A mean reverting level means B1, the absolute value of B1 is less than 1. This is not, which means we probably might have a unit root here. Let's see what we do now. Let's scroll down. So he creates a new series YT, that is the first difference of the log of AstraZeneca's quarterly sales. Remember what we said, if we suspect that we have a non-covariance stationary time series, which that chart really showed that we did, take first differences and replot it and see what you get. Here's what we get. Well, that looks reasonable, right? It looks like there's a mean reverting level. The variance looks like it's well kept within a certain range. So Berglund compares figure 11 to figure 10 and notices that first differencing the log of AstraZeneca's quarterly sales eliminates the strong upward trend that was present in the log of AstraZeneca's sales. Because the first differenced series has no strong trend, Berglund is better off assuming that the differenced series is covariant stationary rather than assuming that AstraZeneca's sales or the log of sales is covariant stationary time series. Yeah, I think you could look at this and say, okay, I think we can feel fairly comfortable that we're dealing with a covariant stationary time series here, as opposed to something like this, which clearly isn't because it is moving off in one direction. All right, what do we do now? Suppose Berglund decides to model the new series using an AR1 model. Berglund uses the natural log of sales in time period t minus the natural log of sales in time t minus 1. That's our dependent variable. It's the difference. Remember, we're using differences, so our dependent is a difference equals to b0 plus b1, and there's the lagged difference. It's still a lagged variable, but remember, we created a new time series that was the difference, that were first differences. So our lagged variable is a lagged first difference. And let's see what we get out of that model. Let's go right to our autocorrelations for the residual. They look okay. Number 1 is a little bit high. Number 4 probably would fail, or would not fail to be rejected, the null. But number 1 looks a little bit high. Let's look at our intercept and our slope. Our intercept is 0.0222, very close to 0, but it's significant. So we can say that it is not equal to 0. And same with the coefficient. It is less than 1, so it is mean reverting. And there we see that it is a difference, and it is significant as well. So let's see what we have here. The lower part of table 11 suggests that the first 4 autocorrelations of the residuals in this model are not statistically significant. With 48 observations, 2 parameters, the model has 46 degrees of freedom. Critical t statistic in this model is above 2 at the 5% significance level. All right, so none of these are over 2. Good enough. None of the t-statistics for the autocorrelations has an absolute value larger than 2. Therefore, we fail to reject the null, that each of these autocorrelations is equal to 0, and conclude instead that no significant autocorrelation is present in the residuals. This result suggests that the model is well specified and that we could use the estimates. Both the intercept and the coefficient on the first leg of the new first difference series are statistically significant. And then there's a couple of questions. We're not going to go into the questions, but I think those are good walkthroughs of those particular problems. Let's go and do some problems at the end of the reading now. Okay, this is question 11. Figure 4 shows monthly observations on the natural log of lightweight vehicle sales. The natural log sales T for the period January 92 to December 2000. So let's have a look at our chart. 92 to 2000. What do we have on the vertical? Millions of units annualized, the natural log in millions of units. All right, and what do we have? We still look like we have something that's trending here. So do we have a constant mean? No. Do we have a constant variance? No. Let me just show you what I mean by a constant mean. Let's say that our time series ended here. Well, we have variance that, sort of looks like that. And let's say that the time series ended here. Well, we have variance from here to here, so all of a sudden our distribution, well, that's a terrible distribution, would look like that. And the mean might be somewhere up here. Here the mean is somewhere down there. Notice that our mean is drifting upwards and our distribution is widening to encompass all our observations. So we do have non-constant mean and non-constant variance. So we cannot go to an AR1 model with this problem. We're going to have to do something. So A says, using the figure, comment on whether the specification as follows is appropriate. No, it's not appropriate. That's exactly what we have here. This is not covariant stationary. So we can say that it is not covariant stationary. State an appropriate transformation of the time series. Well, an appropriate transformation would be to take first differences of the log of sales. If this is the log of sales, take the first difference of the log of sales. So it would be the difference in the log of sales at time period t equals b0 plus b1, and this would be the difference of the lag of the natural log of sales plus the error term. So all we're really doing is we take the first difference first. Now the first differences become our new time series, and then it's just time period t minus 1. It's just a lag first difference because our dependent variable is a first difference. There we go. All right, question 12. Figure 5 shows a plot of first differences in the log of monthly lightweight vehicle sales over the same period as in problem 11. So this is our first differences now. Has differencing the data made the resulting series covariance stationary? Well, there's three things I want to look at: mean, variance, covariance, right? Do I have a constant mean? Well, it kind of looks like it's mean reverting. If I were going to draw a normal distribution on the end, it looks like I do have some kind of mean that is constant. And if I think about variance in a certain way, it looks like I have a contained variance. It looks like I have a finite and constant variance. And I'm seeing that when we're above the line, we're not persisting above the line, but we're dropping below, then we're pulled back above and up and down and up and down. There's not long stretches where I'm above the line and long stretches where I'm below the line. So I can say that my error terms appear to be uncorrelated across time as well. Those three conditions tell me that, yes, I appear to have a covariant stationary time series now. Well, we're going to cover off the next two topics rather quickly here. Section 7 deals with seasonality. Section 8 deals with arch models, autoregressive conditional heteroskedasticity. You'll notice that I'm skipping section 6 altogether, moving averages. And it's not because of any other reason than it's simply not required in the learning objectives. You've got enough to deal with. If we don't have to deal with it, let's not deal with it. It's there if you want it, but I saw no reason in presenting it and tying you up with it because it's a little bit complicated. It requires you to think a little bit differently, and there's no point. So let's go on with seasonality. This couldn't be easier. How do we deal with seasonality? We use a seasonal lag. So let's say that we estimated an AR1 model that looks like this: xt equals b0 plus b1, and there's our first lag, plus an error term. And let's say that we find serial autocorrelation of the error term is not equal to 0. By seasonal autocorrelation of the error term is not equal to 0. And by this we mean that if you're looking at the autocorrelations, let's say 4 quarters back, lag 1, lag 2, lag 3, lag 4, 1, 2, and 3 show no significance, which means we have no autocorrelation, but the fourth one does. Or if you're looking at monthly data, months 1 through 11 show nothing, but the 12th one does. All you have to do is just add a lag at that point in time. So let's say that our fourth autocorrelation for quarterly data showed significance in the autocorrelations, but not the first, the second, or the third. Well, we would just model it like this. Notice we still have our first lag, but would add another term, and there's our fourth lag. And if it were monthly and it was the 12th month that showed significance, we would add a lag for the 12th month. I'll do a walkthrough of the example in the book shortly to show you how that is dealt with there. But before that, we'll do arch models. Again, this couldn't be easier. It sounds difficult, but it isn't. We'll just estimate an AR1 model, like we've done throughout the reading so far. You estimate an AR1 model. And depending on what software you're using, I've always used SPSS. When you run these models, you typically save the residuals, the error terms. So you'll get a new variable in your spreadsheet or in the data sheet where one column will be the new variable, the residuals. You'll then create a new variable for residual squared. So you run the AR1. And the software will give you the residuals. You then create a new variable called residual squared, and you estimate this. You then run a regression of the first lag of the error terms. Notice now this is the error terms. We're just dealing with the error terms from this AR1 model. So what are we doing? We're regressing the estimated squared errors, that new variable that we did on the first lag of the error term, and we're testing. We can use B0 and B1, you could, but rather than confuse it with everything we've done so far, we'll use A0 and A1. You're testing whether or not the coefficient here is equal to 0. If it is equal to 0, rejecting H0, if it is equal to 0, we're good. We're good. Rejecting H0, if we reject it, it implies that we have some heteroscedasticity in the error term. So that's why we're testing the error terms, because that's where it shows up, right? If we have constant variance in the error terms, we have homoscedasticity. If we do not have constant variance, then we have heteroscedasticity. Constant variance would imply that this would be a 0, because what is left over? A constant. As opposed to, if this were non-zero, what we're saying here is that there is some predictability in the variance. We could predict something about the variance based on the last error term, that the error term has some explanatory power for the variance, and that's not what we want. We want this to be 0. So if we fail to reject, we're good. If we reject, it implies that we have an Arch1 model. We have heteroscedasticity in the error term. So let's do a couple of walkthroughs on the examples, and we'll see that this really isn't much. Seasonality, that's easy to deal with. All we have to do is understand, how do we spot seasonality number 1, and how do we deal with it? You add a lag. How do we deal with heteroscedasticity? Well, we test the residuals. And this, I don't want to get too much into detail here, but you really are going to be using some sort of software package, some sort of statistical software, and from that, depending on what you're using, there'll be different commands to save the residuals. You'll then have to create that new variable and run this new term. So there are a few extra coding lines in the software that you'd have to run. This is not part of the output of running an AR1 model. I want to be clear on that. The output of an AR1 model, you can get the residuals. You then have to go back and run a new regression to test A1. You can't just run AR1 and hope to find a test for this for heteroscedasticity of the error terms out of that. You do have to run a separate regression. So we'll do 2 walkthroughs here. Example 15, seasonality in sales at Starbucks, and we're going to see a quarterly seasonal autocorrelation. Now here's sort of the confusing thing if you've been going through this and you get to this point. Typically, if we run an AR1 model, we look at the autocorrelations for any significance, and if we have significance, we have serial correlation, we move on to an AR2 model. But how can we tell whether we have standard serial correlation and should move on to an AR2 model, and whether we have serial correlation representing a seasonal lag? Typically, the process is you would run an AR1 model, look for serial correlation. If you find it, you run an AR2, and you keep going till all the autocorrelation is gone. So if you keep doing that till all the autocorrelation is gone, how do you know when you look at it? How do you say, well, hang on a second, that's not serial correlation. It is, but it has to do with a seasonal lag. Let's not go to an AR2. Let's add a seasonal lag. That's why we want to do a walkthrough through 2 examples to show you what it would look like so that you can recognize it, right? So follow along here. Earlier, we concluded we could not model the log of Starbucks quarterly sales using only a time trend line because the Durbin-Watson statistic from the regression provided evidence of positive serial correlation in the error term. Based on methods presented in this reading, we might next investigate using the first difference of log sales to remove an exponential trend from the data to obtain a covariant stationary time series. Using quarterly data from the first quarter of 95 to the last quarter of 2012, we estimate the following AR1 model using OLS. So we see we have a first difference as our dependent variable equals B0 plus B1 and the lag of the first difference. So everything looks right here. This is an AR1 model. And we have our results. So let's go down and have a look at our results. And again, what do we want to do? We want to go right to the autocorrelations of the residual right away. And we see the first lag, not significant. Second lag, not. Third lag, not. But fourth lag is. Typically when you have something like this where it's not, where you look at your lags and you say, well, it's not, but it is. That's when your eyes should be saying, well, hang on now, we're going back 4 quarters. Let me look at the data. Is there seasonality? Seasonality means that you'll see these sawtooth patterns in the plot of your time series. So you might look at this and say, well, do I have serial correlation and I need to go to an AR2 model? Or do I have serial correlation and I simply need to add a seasonal lag? And here's the way I would look at it. If you have serial correlation in more than one of the lags, go to an AR2 model. If it's only one of the lags and it makes sense that it would be seasonal, so if it were quarterly, you'd see it in lag 4. You'd be looking down, you'd see it in lag 8, you'd see it in lag 12. If it was monthly, you'd see it in lag 12, or wherever it happened, wherever the seasonality happens to occur. Here it happens in the 4th quarter, so we would expect to see it there. If you're only seeing it in one and it matches up with the seasonality, you'd want to add a seasonal lag, run it again, and see if you get rid of that. So let's see what the result here is. First thing to note is the strong seasonal autocorrelation of the residuals. The bottom portion of the table shows that the 4th autocorrelation has a value of 0.7667 and a t-stat of 6.6. With 74 observations and 2 parameters, this model has 72 degrees of freedom. Critical value is about 199. Given this value, we must reject the null that the 4th autocorrelation is equal to 0. So we know that we have significant autocorrelation here. The 4th autocorrelation is the seasonal autocorrelation because this AR1 model is estimated with quarterly data. So that gives you a kind of a hint. If you're estimating a model with quarterly data and the 4th one is significant, you might want to say, seasonality there. Table 13 shows the strong and statistically significant seasonal autocorrelation that occurs when a time series with strong seasonality is modeled without taking the seasonality into account. Therefore, the AR1 model is misspecified. We should not use it. So look at what we model next. There again is our dependent variable. It's just the first difference equals B0 plus B1. It's a first difference, and this is the lag of the first difference, and we add the t minus 4, t minus 5. That is the 4th lag. Notice what you have to do now. To get the first lag, it is t1 minus t2. To get the 4th lag, it is t4 minus t5. And let's see what happens to our new output. So this is the output that we'll get. Notice that we have the intercept and the 2 slopes in here. And let's go down here and have a look. And yes, look at that. We got rid of it because our t-statistic, recall, is right around 199 or 2. This is negative 1.76. So this is no different than 0. So we're fine with that. We've gotten rid of it. We have no serial autocorrelation left over. We don't have to go to an AR2 model. The seasonal lag did just fine. We can then use these coefficients to do some forecasting if that's what we choose to do. All right, let's look at one that has 12 months of data. I'm not going to bother reading the narrative. Let's just go right to the output and have a look at what we'd be looking at. So let's go right to the autocorrelations of the residual. We have 12 lags. Here's our autocorrelation, standard errors, and our t-statistics. So we have one here in lag number 2 that looks significant. We have another one in number 6. Looks like there's one in number 7 that probably could be. There's one in number 10. And there's a lag in number 12. So what do we do here? Do we say, well, you know what, there's autocorrelation in more than one period of time, but there is definitely a seasonal autocorrelation over here. Do I get rid of all of the serial correlations first and then deal with the lag? Or do I get rid of the lag and see if it clears this up? I would proceed by saying, I clearly have a lag. I clearly have seasonality. I clearly have that. So no matter what model I get to, I'm going to have to deal with the seasonality. Even if I go to an AR2, I'm probably still going to have seasonality and I'm going to have to deal with it. So let me deal with it right away and let's see if it clears anything up. If it doesn't, then I'll go to an AR2 model. But as it stands right now, if I didn't know anything about seasonality, I'd be going to an AR2 model. But because I know of seasonality, I can look down and say, well, now hang on a second. I'm going to have to deal with this. Let me deal with it right away. So let's see how we deal with it. Here's the next model. Notice here's the 12th, the lag for the 12th month. And let's have a look at what we have on the way down. And we've just estimated the same thing, except we put a seasonal lag in. We didn't go to an AR2. We just put a seasonal lag in. And have a look at our T statistics here. And if we look down, we see that we solved a lot of those problems. A lot of them went away, including the 12th lag. So sometimes, if we look and we find serial correlation and a seasonal lag, taking that seasonal lag or adding a variable to that seasonal lag may clear it all up. Now in this case, it did. We don't have to go to an AR2 model. We have a well-specified model at this point. All right, let's take a look at the idea of conditional heteroscedasticity, the non-constant variance in the error term, and how we test for ARCH1 here. And we've seen this example before. We're revisiting Lisette Miller. She wants to test whether monthly data on CPI inflation contain autoregressive conditional heteroscedasticity. And you'll recall she took a 30-year time period on inflation, and her colleague pointed out that, listen, it looks like you got two different regimes in here. And even when we looked at the data, it did look like the variance did change sometime. From my eyeballs, it looked like it changed around 2003, 2002. But let's just see what we have here. Based on the analysis in examples 6 through 9, she has concluded that if she modeled monthly CPI from 84 to 2013, there is not much difference in the performance of an AR1 and an AR2 model. And you recall we did that. We looked at an AR1 model for the full period of time, and we looked at an AR2. We looked at the root mean squared error and saw that, well, the AR2 didn't really improve it that much. And that's what she's noting here. There's not much difference in the performance. The AR1 model is clearly better for the period 2007-2013. She decides to further explore the AR1 model for the entire period 84 to 2013. Table 17 shows the results of testing whether the errors in that model are ARCH1. Remember, to test ARCH1, what are we doing? We're running an AR1. We're saving the residuals. We're then squaring the residuals and regressing that against the first lag of the error term. So the intercept, and here, of course, is our first coefficient, well, the coefficient that would go with the variable, which is the estimated value, t minus 1. It's one lag behind, right? And here are our t statistics. We have a significant t statistic. So let's see what we have. The t statistic for the coefficient on the previous period squared residuals is greater than 4.1. Therefore, Miller easily rejects the null hypothesis that the variance of the error term does not depend on the variance of the previous errors. Consequently, the test statistics she computed in Table 5 are not valid, and she would not use them in deciding her investment strategy. Again, what have we done? We've taken those 30 years where, just from eyeballing the graph, it looked clear that we had two different time series regimes in there. So she took the AR1 model for those 30 years and said, well, let me actually be certain. Let the data tell me that that's true. She ran the AR1 model, saved the residuals, created a new variable, which is the residual squared, and regress the residual squared on the first lag of the residual squared. Notice this is the estimated, E hat, the error term, estimated squared, lagged. Found that we had a significant test statistic. Because we do, there is some explanatory power on the error term for predicting the variance in the next period, which means we have heteroscedasticity. If we did not have that, this would be 0, and what would be left? The intercept, a constant. The variance would be a constant. So let's just do a little bit of reading because we're going to run another model here. It is possible Miller's conclusion that the AR1 model for monthly inflation has arch errors in it may have been due to the sample period employed, 84 to 2013. In example 9, she used a shorter sample period, 2007-2013, and concluded that monthly CPI follows an AR1 process. So the question is there an ARCH1 process in that model? Well, let's find out. So you run that again. She ran the AR1 model just for February 2007 to December 2013, saved the error terms, created a new variable, which was the error term squared, and ran this regression. Notice that the t statistic on the coefficient for this variable is not significant. which means it is no different from 0. If it's no different from 0, all we have is the A naught, the constant, the alpha term, or the B naught term, depending on how you want to interpret it, which means the variance is a constant. So we fail to reject the null hypotheses. The coefficient is equal to 0, and we do not have conditional heteroscedasticity. So we're good. Question 13. Using monthly data from January 92 to December 2000, we estimate the following equation for lightweight vehicle sales, and this is the equation that we've estimated. Table 5 gives sample autocorrelations of the errors from this model. We have 12 lags, the autocorrelation standard error, and the t-statistic. What jumps out at you here? Look at those t-statistics. I don't even think we even need to calculate a critical value. These are all significant. We have autocorrelation, most definitely. So let's see what we have. A, use the information in the table to assess the appropriateness of the specification given by the equation. Well, that's the specified model we used. How appropriate is it? Not appropriate at all. You'd have to modify this model before continuing. How would you modify this model? Well, you can move on to an AR2 model, right? B, if the residuals from the AR1 model above violate a regression assumption, how would you modify the AR1 specification? Well, you could estimate an AR2 model and run these autocorrelations again and have a look at the t-statistics. If they're still serially correlated, you'd move on to an AR3. If they're not, you may want to look down and say, well, what are we modeling here? We used monthly data, so I'd want to look at number 12, and if all of these are not significant but 12 is, I may have a seasonality component in there. I may want to lag that one, so I'd want to check that first. After I'm done with that, I may want to save the residuals from this run, square them, and test for Arch1, an Arch1 process to see if I have any heteroscedasticity in there. If I'm clean on the serial correlation, if I'm clean on seasonality, and if I'm clean on Arch1, I've got a properly specified model. All right, we're on question 14. I had to break question 14 up across 2 screens because it was just too big to put on one and I didn't want to shrink it. So let's have a look at what we have. Figure 6 shows the quarterly sales. So I know I'm dealing with quarterly sales of Cisco systems from Q1 91 to Q4 2000. So my fourth quarter is the last quarter. Quarterly sales, and what have I got? Look at this. This is in sales. So it doesn't look like I have a linear trend here. It looks like I have an exponential trend. Let's look at the second part of question 14 to see where we go from here. All right, so table 6 gives the regression statistics from estimating the model, and we are using the log of sales, which we thought we would because we did have an exponential trend. And it's one lag, an AR1 model, and here's our output. Change in the natural log of sales for Cisco, quarterly observations. All right, let's see what we have. Describe the salient features of the quarterly sales series. So it's asking us to describe the features of that sales series. Well, remember, it looked like this. And when it's asking a question like this, what are the salient features? Sometimes you look at it and go, well, what do you mean? Well, all it's asking is, what did you see? And you just want to answer it in terms of what we're doing. Well, we didn't see a linear trend. We saw an exponential trend, not a constant growth trend, but a constant growth rate trend, which means we're probably going to use the log of sales as opposed to using just raw sales data. That is pretty much what you're going to find on any sales series. If sales is the series you're looking at, you're pretty much going to find that you're using a natural log of that series. B, describe the procedures we should use to determine whether the AR specification is correct. Well, we ran the AR specification. We have our t-statistics. They look like the intercepts are significant. This intercept is well below 1, so maybe we don't have a unit root. Where would we go from here? Well, the first thing we do is what? We go to the autocorrelations. We find out whether or not any of the error terms are serially correlated. We're looking, and if they're not, we're still looking for a seasonal lag. Maybe there's a seasonality in there and we want to correct that. Once that's done, we can then save the residuals, create that new variable, residual scared, and test for ARCH1 process. And if we have no ARCH process present, you can conclude that you have a properly specified AR1 model. C, assuming the model is correctly specified, what is the long-run change in the log of sales toward which the series will tend to converge? So it's asking for the mean reverting level. And remember, our mean reverting level is rather easy to figure out. B0 over 1 minus B1. And minus B1. So what do we have for our B0? Our intercept is 0.0661. 1 minus, what's our B0? 0.4698, and it is a positive 1, so we do subtract this time. And if you take your calculator out and hit a few keys, you'll get 0.1247. 0.1247. Now, keep in mind, what is this? This is the mean reverting level for this value. It's the mean reverting level for that value. All right, we're on question 15. Figure 7 shows the quarterly sales of Avon products from Q1 92 to Q2 2002. Describe the salient features of the data shown. So what do we have here? Well, this is the second quarter of 2002. So what we can do is you can look, this is obviously the second quarter of 2002. That's the first quarter of 2002. That's the fourth quarter of 2001. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And you see this little sawtooth in there. So there is heavy seasonality going on in there. Not only that, we tend to have a upward rising trend. I don't know whether you'd want to say that that is linear or it's log linear. We're not really sure. It's asking us to describe the salient features of the data. The two big things that I see right away, upward trend. We have an upward trend, so this is not covariant stationary, and I see seasonality. And this is just from plotting the series first. Before we do anything with it, we plot out the series. Notice it's just in raw millions of dollars, and you have a look and you say, well, okay, I know where I got to go from here. I have an upward trend. I don't have a covariant stationary time series, and I see seasonality. So it sort of gives you an idea of the things you're going to have to deal with. That was it for 15. All right, question 16. Table 7 below shows the autocorrelations of the residuals from an AR1 model fit to the changes in the gross profit margin of the Home Depot. Yeah, so here's our autocorrelations. What do we have here? Leg 1, leg 2, leg 3, leg 4, leg 5. Look at leg 4 here. This is the autocorrelation, by the way. This is not the T statistic. This is the autocorrelation, 0.8496. Autocorrelations of the residual from estimating the regression. What do we have? Q1 1992 to Q4 2001. We have 40 observations. So we would divide all of these, basically, you can divide by 1 over root 40. And when we do it with this one, you'll find that this one is going to be significant. You'll get 5, where's my notes? 5.37. So it is significant. It's in the fourth. This is Home Depot, fourth quarter. Does that make sense? Does that make sense for us? And this is all the way to the fourth quarter of 2001. So the fourth lag would be the last fourth quarter. So we do have seasonality going on at a fourth lag. Table 8 shows the output from a regression on changes in the gross profit margin for Home Depot, where we have changed the specification of the AR regression. And here is the output. So the specification has changed. Identify the change that was made to the regression model. Well, what did we estimate first? This is our B0 plus, and even though it's negative, we'll put plus. We have B1 and the change in GPM lagged, T minus 1 plus the error term. And now we have a T minus 4, not just a T minus 1 lag, T minus 4. So this is what's new, is we have a seasonal lag. So that is the change that was made to the regression model. The next question says, discuss the rationale for changing the regression specification. Discuss the rationale for doing this. The rationale for doing that is this. You had, if you check each one of these, you'll find not significant, you'll find not significant, not significant, significant and not significant. So being that you only have one, and it is at a seasonal lag, or at least a theoretical seasonal lag, fourth quarter for Home Depot. Okay, well, maybe Christmas, power tools, things like that, right? Then once the seasonal lag was entered in, what do we have? It seemed to, well, we don't have any of the autocorrelations. We're just wondering, the question is just saying, what's the rationale for doing that? Well, that's the rationale for doing it. There we go. Question 17. Suppose we decide to use an autoregressive model with a seasonal lag because of the seasonal autocorrelation in the previous problem. We are modeling quarterly data, so we estimate equation 15. What do we have here? We have the log of sales. We have the first differences in the log of sales is equal to B0 plus B1. And we have the first lag plus a B2 coefficient. We have the fourth lag. There's our seasonal lag. Table 9 shows the regression statistics from this equation. So here's our regression statistics, our intercept, coefficient, standard errors, t-statistics. Here's our autocorrelations. Let's have a look. Look at that. Nice and clean. No serial correlation here. We're good to go. Now, we don't know whether we have an Arch1 process here. This is not telling us if it tested for that. We'll just assume that that's not part of this question. A, using the information in Table 9, determine if the model is correctly specified. Well, it looks like it. Again, we don't have a result for an Arch1 process test, so we'll assume that it was clean, and we'll take it as it is. Yes, I would say that we have a correctly specified model at this point. B, if sales grew by 1% last quarter and by 2% 4 quarters ago, use the model to predict the sales growth for this quarter. This can be tricky because what have we got? We've got differences and we've got natural logs, and we're asking to predict a sales growth. So you have to try to work your way backwards in that and see what it means. So let me see if I can help you kind of clear this up a little bit so that you can see it in your head as opposed to me just writing it down. What we're saying is that if sales grew by 1% last quarter, so they grew 1% last quarter, and they grew 2% 4 quarters ago. 2% 4 quarters ago. So because we're dealing with differences and we're dealing with the log of the differences, that 2% is going to cause us some trouble. Let's see if we can't figure out what that means. So let's just use a hypothetical example. Let's say sales were $8,500 and they grew 2% to $8,670. They grew to $8,670. Well, there's sales. What we want to do is we want to take the log of sales, and since we're dealing with first differences, we want to subtract. So if we took the log of 8670 minus the log of 8500, we would get 0.0198. So that means that the first difference resulting from a 2% growth would be 0.0198. 0.0198. Well, how do we deal with that? Well, if you took the anti-log of that, in other words, you hit second function on your calculator and you hit ln, because above ln is e to the x. Here's what you would get. You raise that e to the x, you get 1.02. Well, 2%, 1.02. And if you did the same thing as an example for 1%, what you would find is it would give you 1.01%. So great. All we have to do is just use the 1.2 and the 1.01. Let me show you how that's done. So what we want to do is we want to calculate, we want our dependent variable, and we have all of our coefficients here. So let me see if I can give it to you here. It would be 0.0121, that's a minus 0.0839 log of 1.01. Why the log of 1.01? Well, because I've just shown you that if you take the log of 1.02, it'll get you back to what a first difference would have been if you modeled a 2% growth quarter over quarter. 8,500 to 8,670, that's 2% growth. That 2% growth means that we have a first difference in the log of 0.0198. How do we get a first difference in the log of 0.0198? You take the natural log of 1.02, you will get that. So to get the first difference on this log, we take the log of 1.01. It'll give us what the first difference would have been, and that's the coefficient associated with the first difference. And then we have a plus. This is 0.6292, and we'll use log 1.02. And what will we get here? We will get equals 0.0121 minus 0.000, trying to follow my notes correctly here, whoops, 0.000834, 833 plus 0.012459813 will give us 0.02372. But that's a first difference. That gives us the first difference. We're asked for what the growth, the sales growth rate is. So all we do is we raise it, e to the power of this, and of course you'll subtract 1 to get a growth rate, and if you raise this, raise e to the power of the first difference and subtract 1, you will get 2.4%. So this model, with these growth rates at those lags, would end up being 2.4%. Now, here's what I got to say about this. That's the hardest part. This is all easy stuff, but once you start transforming a variable, you take the natural log of it. Once you start taking first differences and using that in the regression, working your way backwards, you have to remember that these are differences, not amounts. These are natural logs, not raw data. So if you want to work your way back, you have to be able to see clearly in your head how each of these numbers work. That, what we just did here, that is the trickiest part of what you have to do. I'll be honest with you. There are times where I've got to stop after I look at one of these things and I say, okay, how do I get back to where I started? And the way I get back to where I started is I think, well, let me get here first, and then I know my way back. So I get here by leaving a trail of breadcrumbs, which is, well, okay, well, let's say that sales were 85 to 86. There's 2%. Let me work my way this way. Aha, I see what I'm doing. Plug that in, and then I can work my way back. However you do it, maybe you see it clearly. Maybe you can look at this and go, yeah, I didn't need to do all that. I could see that that was the right way. Well, you're better than I am at this then. 18's nice and easy. I probably could have made it bigger, but here it is. Describe how to test for autoregressive conditional heteroscedasticity, ARCH, in the residuals from the AR1 regression on first differences in the civilian unemployment rate. So this is the AR1 model that we did. How do we test to see if there's an ARCH1 process going on? Well, it all comes down to the residuals. We save the residuals, and we create a new variable called residual squared. Residual squared, and that'll give us a whole new column. Typically, when you're looking at your data entry sheet, they'll look like this, and you'll have the names of your variables across here. And when you create a new variable, it gets added to the end. You'll have your residuals, all your residuals here. You'll create a new variable called error squared, and that will all be down there. And this is what you'll tell SPSS. This variable name is what you'll tell SPSS you're looking at. And then what you want to do is you want to calculate this regression. E squared equals A naught plus, actually, let me make that a little bit better so we see it. A naught plus A1, here we are, squared, and that's estimated, T minus 1 plus some error term. And then you want to test A1 equal to 1, equal to 0. You want to test A1 equal to 0. If A1, and here's the thing, you do not want to reject. You want to fail to reject. Fail to reject. And here's the logic behind failing to reject. If you fail to reject, then A1 is no different than 0. And if this is 0, this whole term falls off. And if this whole term falls off, what is your variance? Your variance is going to be a constant. So there we go. That's how you would test for an ARCH1 process. Right, this is the last topic in time series we have to get through. Regression with more than one time series. Not really that difficult. If you got a firm footing on where we've been so far, this really isn't that much more difficult. So let's have a look. If any time series in a linear regression has a unit root, OLS t-stats may be invalid. So what do we have to do? If we're using two time series, let's say one is an independent variable and the other is the dependent, you test each time series using the Dickey-Fuller test. You use that to test for a unit root. And you'll have a couple of options here. A, both reject H naught that B1 equals 1. In other words, neither one has a unit root. You're good to go. B, you'll reject H naught for the independent variable, but not for the dependent variable. And of course, C is the same thing, just in reverse. It's you'll reject it for the dependent, but not for the independent. In other words, B and C are saying one of them has a unit root, the other one doesn't. The error term would not be covariance stationary, either because it has a non-constant mean, or because it has non-constant variance, or because it has correlated errors. So your regression coefficients and your standard errors would be inconsistent. So far we can see that the best one so far is no unit roots. If one of them, and only one of them, has a unit root and the other one doesn't, we got a problem. D, both series have a unit root. Now you would think that that's a real problem, but it's not. It can be, but it doesn't necessarily have to be. We then have to ask the question, are they co-integrated? Well, what does that mean? It means they share a common trend. A long-term economic or financial relationship exists between them such that they do not diverge from each other without bound in the long term. If they are co-integrated, we're good to go. If they're not, we have a problem. So, either neither series has a unit root, we're good to go, or either both series have a unit root, they are co-integrated, we're good to go. Anything else? We cannot move further. I've gone ahead and written at the top of the screen here, both have a unit root, no co-integration, same results as B and C earlier, options B and C, you cannot proceed further. And I should clarify that. It's not that you can't proceed further, it's just you can't proceed further with the tools that we've used up to now, with OLS. You have to stop. You get into more specialized models at that point. That's not required knowledge at this level, but in your profession, depending on the tools that you're going to use and how quantitatively driven you are, you may bump into this problem at some point. Be aware that you'll have to continue your education at that point. So there are only two options that offer valid regression results. The favored one, number one, no unit roots in either series. We've used the Dickey-Fuller test on each. We found that result. We're good to go. We're clean. Nothing more has to happen. Two, both have unit roots but are co-integrated. Well, we know how we can find out if they have unit roots. We have the Dickey-Fuller test. But how do we test for co-integration? Well, that's down here, and I'll get to that in a second. But first, a caution on the regression output. If we find that we do have co-integration, we're good to go. But the output has a different interpretation. The regression will estimate long-term relationships between the two. It may not be the best model of the short-term relation. So let's look at this test for co-integration. What we're basically going to do is we're going to perform a Dickey-Fuller test, but on the error terms. We're going to look for a unit root in the error terms. So, to get the error terms, what must we do? We must first estimate the model. So we run the regression, we save the error terms. We're running this for the sole purpose of getting the error terms. We get the error terms. We're going to use a modified Dickey-Fuller test, the Engle-Granger Dickey-Fuller test, to test the hypotheses that G equals 0. Remember, testing for a unit root, right? So what are we testing? First differences against first lag. First difference of the error terms equals B naught plus G, and the first lag plus some error term, and we want to test whether or not G is equal to 0. You got to use different t-values than the Dickey-Fuller. This is a modified, since we're using the error terms of the regression and not the actual data from the time series itself. We're going to need different t-values. That's what's beautiful about your statistical package. If you tell it you want the EGDF test, and not just the Dickey-Fuller test, but it knows, if you tell it you want this, it knows that it has to use the residuals, it knows that it has to run this, and it knows to use different t-values. So you're really looking to interpret more than you are to calculate. You can't calculate this stuff, by the way. You simply can't. So you need to be able to interpret the results. The statistical package will run everything for you. You gotta be able to tell it what you want it to do. Hey, look, I want this test, and I want this, and I want that, and then interpret the output. So if you fail to reject H naught, there is no co-integration, which means you go all the way back up here. Both have a unit root, no co-integration. You got to stop. At least you got to stop doing things the way we're doing things now. You reject H naught, therefore they are co-integrated. Regression output will be okay, but again, that caution comes into play. Right, and last note here, what if we're using more than one independent variable time series, and not just an X, not just Y regressed on X, but Y regressed on X and Z? Well, A, use a Dickey-Fuller on all of them. Hopefully there are no unit roots, you're good to go. B, at least one has a unit root, one does not. Again, you cannot use OLS. You got to stop, not so much stop, but stop using what we're doing and move on to something else, which we're not going to do. Or C, all have unit roots. What do? You test for co-integration, except you run this model to get these error terms. Oh, you're doing the same thing. It's just a test of the unit root of the error terms, except you run the full model. Now you're running with all the series. And you test this again, and you're also testing the hypotheses that G equals 0. If you fail to reject, you have no co-integration. You cannot use OLS, just like we did with 2 time series. If you reject, OLS is okay, but it starts to require much more work. Let's not get into the extra effort that you're going to need on this one. Let's just say that the process is the same. If they all have unit roots, you test for co-integration. You test the same way. If it's okay, you can continue, but there are big cautions. We'll leave that for a time when you actually need it in practice. It's not required to take this much further than that end statement there. All right, question 19. Suppose we want to predict the annualized return of the 5-year T-bill using the annualized return of the 3-month T-bill with monthly observations from January 93 to December 2000. So it looks like we have 2 time series here. We have a time series of 5-year bills, the monthly returns of 5-year T-bill, and the monthly returns of the 3-year T-bill, and we want to predict the 5-year based on the 3-month. Our analysis produces the data shown in Table 10. R-squared, standard error, observations, Durbin-Watson. Well, that's an ugly Durbin-Watson, right? What do we got? An intercept, a 3-month coefficient, and they look highly significant. Can we rely on the regression model in Table 10 to produce meaningful predictions? Specify what problems might be a concern with this regression. Well, what is our y and what is our x? They are both time series. So before we did this, we should have used the Dickey-Fuller to test for a unit root. And if neither one of them had a unit root, we're good to go. Excellent. If one of them had a unit root and the other one didn't, you got to stop. If they both had a unit root, let's say they both unit root, and what do we do there? You test for co-integration. And what do we want to find? We want to find co-integration. So if we find co-integration, we're good to go. If we don't find co-integration, we must stop. So what problem might be a concern with this regression? Either the big problem is one, but not the other, has a unit root, or they both have a unit root and they're not co-integrated. That wraps up the questions. So back at the beginning of the reading, I sort of gave you a bit of a roadmap of where we were headed. Now let's have a look at the roadmap of where we've been, and you'll see that it kind of categorizes things and puts things in order. So whenever we're lost, we always like to look at a map. This is a nice map. So let's say that we're starting our analysis. We have a choice. We can look for causal relationships, a series of observations on X that help us predict Y. Or we could just look at time series analysis. And for time series analysis, recall we need covariance. I gotta work on that. Covariance stationary time series. If we do have a covariance stationary time series, yes, we have a choice. We can use a linear or a log linear model. Then if we run the linear or log linear model, we're looking for serial correlation in the error terms. We're testing dw equals 2. Yes, it does equal 2, means we have no serial correlation, we're okay. No means we have serial correlation, we're going to have to move on to an AR1 model. If, back here, we do not have a covariant stationary time model, we'll transform the data, maybe first differences, and then we'll check again, is it covariant stationary? And then we head down this pathway again. Typically, you'll head down this pathway, more than likely you'll end up down here, you'll have an AR1, which again must be covariant stationary. You'll run it. Serial correlation, no serial correlation. If you have no serial correlation, you're good to go. Serial correlation, you have 2 choices. Move on to an AR2, depending on the significance of the errors. If they happen to be just at a lag, you'll add a seasonal lag. But if there's more of them and they're not just located on the lag, after you add the seasonal lag, if they don't go away, you'll go from an AR1 to an AR2. If you have no serial correlation at an AR2, you're good to go. If you add the seasonal lag and you get rid of serial correlation, well, we keep going. Next, we would test for ARCH1 process. And again, you're testing the error terms here, and the test is that A1 is equal to 0. If you fail to reject, you're good to go. If you reject, you got to move on to something called generalized least squares. So this is a sort of a nice route through it. Typically, this is probably the process you would follow. You'd find covariance stationary. You'd have to get that first. You'd head down here and you'd find out that you'll end up over at AR1. If there is a serial correlation or autocorrelation in the error terms, you're most likely going to add a seasonal lag, and that pretty much would clear it up. If it doesn't, you'll move on to the AR2. Once you clear that up, then you can test for an ARCH process, and if you don't find one, you're okay. That's time series. In this whole reading, there was only a couple, I think 1 or 2 things that you had to calculate. The rest really was explain. So you have to understand how to interpret that regression output and the process that you go through. This will help you out a lot.